You are being held together by something invisible, right now, this very second. The galaxy you are standing inside is spinning at 600,000 miles per hour, and every star, every planet, every atom of gas should have been flung into the void billions of years ago. The math is not close. It is not a rounding error. By every law of physics we have tested and trusted for centuries, the Milky Way should have torn itself apart before Earth ever formed. And yet here you are, here we are, rotating through space in a structure that has no right to exist. The only reason it does, the only reason galaxies exist at all, is because of something we cannot see, cannot touch, cannot detect with any instrument ever built. Something that does not emit light, does not absorb light, does not reflect, refract, or interact with electromagnetism in any measurable way. And yet it outweighs every star, planet, and galaxy combined. 85% of all the matter in the universe is invisible. We call it dark matter, and it is not a theory, it is an observation. A fact written into the motion of galaxies, the bending of light around massive clusters, the very architecture of space-time itself. Astronomers discovered it by accident in the 1970s when they realized galaxies were moving far too fast to be held together by what we could see. Since then, we have mapped its gravitational fingerprints across the cosmos, traced its influence through billions of light years, and sent experiments miles underground to catch even a single particle of the stuff. We have found nothing, and yet without it, none of this works. Not galaxies, not stars, not you. So what is it? Where is it? And why, in an age when we can photograph black holes and detect ripples in space-time, can we not find the thing that makes up most of the universe? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Tonight, we trace the case from its earliest warnings to the experiments and surveys now reshaping the search. And at every scale, one question returns: are we approaching a hidden substance, revising gravity, or confronting something deeper still? There is a rule in physics that has held steady for more than 3 centuries. It is simple, it is elegant, and for most of human history, it has worked beautifully. The rule is this: the gravity an object exerts is directly proportional to the amount of mass it contains. More mass, more gravity. Less mass, less gravity. Newton figured this out in the 1600s, and Einstein refined it in the early 1900s. But the core principle never changed. Gravity is honest. It tells you exactly how much stuff is there, except when it doesn't. In the early 1930s, a Swiss astronomer named Fritz Zwicky was studying a region of the sky called the Coma Cluster. It's a massive gathering of more than 1,000 galaxies sitting roughly 300 million light-years from Earth. Zwicky was trying to do something straightforward: weigh the cluster. Not literally, obviously, but by measuring how fast the galaxies inside it were moving, he could calculate how much mass the cluster needed to hold itself together. Galaxies orbiting inside a cluster behave like rocks swung on strings. The faster they move, the stronger the gravitational pull required to keep them from flying apart. Zwicky measured the speeds. They were high, very high. Then he added up all the visible stars in all the galaxies he could see, estimated their total mass, and did the math. The numbers did not match, not even close. The galaxies in the Coma cluster were moving so fast that the visible matter, all the stars and gas Zwicky could account for, made up only about 1% of the mass needed to hold the cluster together. 1%. The other 99% was missing. Zwicky called it dark matter. Not because he knew what it was, but because whatever it was not glowing, it was not emitting light, it was not showing up in any telescope. And yet it had to be there, because without it, the Coma cluster should have torn itself apart billions of years ago. The galaxies should have scattered into the void like billiard balls after a break. They did not. They stayed together, bound by gravity from something no one could see. Zwicky published his findings in 1933. The scientific community nodded politely and then mostly ignored him. The man had a reputation for being difficult, and his conclusions sounded absurd. 99% of the universe's mass, hiding in plain sight, invisible to every instrument humanity had ever built. It was easier to assume he had made a mistake. Maybe he miscounted the galaxies. Maybe his velocity measurements were off. Maybe the cluster was younger than he thought, and the galaxies just had not had time to escape yet. There were plenty of ways to dismiss the problem without invoking an entirely new kind of matter that refused to interact with light. For decades, that is exactly what happened. Zwicky's missing mass problem sat on a shelf gathering dust while the rest of astronomy moved on. World War II happened, the space race happened, quasars were discovered, pulsars were discovered, black holes went from theoretical curiosities to confirmed objects. And through all of it, Zwicky's dark matter remained a footnote, an oddity mentioned in passing and then forgotten. Then, in the 1970s, a scientist named Vera Rubin started looking at galaxies differently. Rubin was an astronomer at the Carnegie Institution in Washington, D.C. And she was not studying clusters. She was studying individual spiral galaxies, the kind with graceful arms curling outward from a bright central bulge, galaxies like our own Milky Way. She wanted to know how fast the stars in those galaxies were moving as they orbited the galactic center. This was not a new question. Astronomers had been measuring galactic rotation for years, but Rubin had access to better instruments, and she was looking at the outer edges of galaxies, the dim regions far from the bright core where earlier observations had been harder to make. What she found made no sense. In a solar system, objects farther from the center move slower. Mercury races around the Sun in 88 days, Earth takes 365, Neptune takes more than 164 years. The further out you go, the weaker the Sun's gravity becomes, and the slower the orbital speed. That is how gravity works. That is what Newton's laws predict. And for centuries, that prediction has matched reality perfectly. Galaxies should behave the same way. Stars near the galactic center, where most of the visible mass is concentrated, should move quickly. Stars farther out, in the sparse outer regions where the light dims and the density drops, should move more slowly. The rotation curve, a graph plotting orbital speed against distance from the center, should slope downward as you move outward, a smooth, predictable decline. Rubin's rotation curves did not slope downward, they stayed flat. Stars at the outer edges of galaxies were moving just as fast as stars near the center. In some cases, they were moving even faster. The galaxies were spinning like rigid disks, as if all the stars were glued to a single rotating plate. That is not how gravity works. That is not how anything in the known universe works. Unless there was more mass out there than anyone was counting. Rubin and her colleague Kent Ford measured galaxy after galaxy, Andromeda, Triangulum, dozens of spiral galaxies scattered across the sky. Every single one showed the same pattern, flat rotation curves, stars moving too fast, gravity pulling harder than the visible matter allowed. By the late 1970s, the evidence was overwhelming. Zwicky had been right. There was mass in these galaxies that no one could see. A lot of it, roughly 5 to 10 times more dark matter than visible matter, spread throughout each galaxy in a vast invisible halo extending far beyond the edges of the starlight. The implications were staggering. Every galaxy humanity had ever observed, every elegant spiral and every dense elliptical was embedded inside a cocoon of invisible material. The stars we see, the gas clouds, the nebulae, the bright cores, all of it represents a tiny fraction of what is actually there. The rest is dark, silent, undetectable except through its gravitational grip. This was not a small correction. This was not a minor adjustment to the models. This was a complete rewrite of the cosmic inventory. Take everything you can see in the universe. Every star, every planet, every comet, every speck of dust drifting through intergalactic space. Add it all up. Now multiply by 5. That is how much more matter exists that you cannot see. The universe, it turns out, is built mostly out of things we have never touched, never photographed, never directly measured. We only know it is there because of what it does. NASA calls dark matter the invisible glue that holds the universe together. The University of Chicago describes it as like an invisible poltergeist that we track only by its effects. CERN notes that researchers infer its existence solely from its gravitational influence on visible matter. These are not poetic exaggerations. These are the most accurate descriptions scientists have. Dark matter does not absorb light. It does not reflect light. It does not emit light at any wavelength we have ever searched. It is transparent to electromagnetic radiation in every form. Visible light passes through it. Radio waves pass through it. X-rays pass through it. As far as light is concerned, dark matter might as well not exist. Gravity, however, knows it is there. The missing mass problem is not a theory, it is not a model, it is a direct observational mismatch between the amount of matter we can see and the amount of gravity we can measure. The galaxies are moving, the clusters are holding together, the gravitational lensing, which we will get to in the next chapter, is bending light in ways that require mass. The mass is real, it is measurable, we just cannot find it with any telescope ever built. By the early 1980s, Rubin's work had transformed dark matter from a fringe hypothesis into mainstream cosmology. The rotation curve problem was too consistent, too widespread, and too well measured to dismiss. Zwickie's coma cluster, once an isolated anomaly, was now recognized as an early glimpse of a much larger truth. The missing mass was not missing, it was there all along. We were just looking for it in the wrong way. The current cosmic breakdown goes like this. Roughly 5% of the universe is ordinary matter. Protons, neutrons, electrons, the stuff that makes up stars and planets and you. 27% is dark matter. 68% is dark energy, a separate mystery that we are not addressing in this video. If you add up all the matter in the universe, both ordinary and dark, about 85% of it is dark. We live in a universe where the vast majority of the material holding everything together is completely invisible. Think about what that means for a moment. You are standing on a planet made of ordinary matter. That planet orbits a star made of ordinary matter. That star is one of hundreds of billions in a galaxy held together primarily by dark matter. The galaxy itself is embedded in a halo of dark matter that extends hundreds of thousands of light years beyond the visible edge. And you, standing there on your ordinary matter planet, have no direct way of detecting the scaffold your entire galaxy is hanging from. The first time you learn this, it feels like someone moved the furniture while you were asleep and forgot to tell you. Everything looks the same. The stars are still there, the galaxies still shine, but the foundation underneath has shifted. What you thought was solid ground turns out to be a thin raft floating on an ocean of something no one understands. Vera Rubin spent much of her career trying to make sense of that ocean. She was careful, methodical, and uninterested in hype. When reporters asked her what dark matter was, she would tell them honestly that she did not know. When they asked her if it was exotic particles from another dimension, she would shrug and say maybe, or maybe it is something simpler that we just have not thought of yet. What mattered to Rubin was the data. The rotation curves did not lie. The galaxies were behaving as if they contained far more mass than we could see. Whether that mass turned out to be strange new particles or some overlooked population of ordinary objects was a question for the particle physicists and theorists to sort out. Her job was to measure, and the measurements all pointed in the same direction. She was not the only one. By the 1980s and 1990s, teams around the world were refining the observations, extending the measurements to fainter galaxies and more distant clusters. The flat rotation curves held up. The missing mass estimates held up. Dark matter went from controversial to unavoidable. It became the default assumption in every model of galaxy formation, every simulation of cosmic structure, every calculation of how the universe evolved from the hot, dense state of the Big Bang to the sprawling web of galaxies we see today. And yet, for all that acceptance, the nature of dark matter remained a complete mystery. Still does. We know how much of it there is. We know where it is. We know how it behaves on large scales. We know it clumps around galaxies. We know it does not interact with light. We know it exerts gravity. Beyond that, we are guessing. The rotation curve problem did not just reveal the existence of dark matter. It revealed the limits of observation. For thousands of years, astronomy was the study of light. If something glowed, we could see it. If it reflected sunlight, we could photograph it. If it emitted radio waves or X-rays, we could detect it. Dark matter broke that rule. It forced astronomers to admit that the universe contains vast reservoirs of material that will never show up in a picture, no matter how long the exposure or how sensitive the camera. That realization changed the field. It forced cosmologists to start thinking like detectives instead of photographers. You cannot see dark matter directly, but you can see what it does. You can watch how galaxies spin. You can measure how clusters hold together. You can observe how light bends as it passes through regions of space where dark matter is concentrated. Each clue adds a piece to the puzzle. None of them give you a clear picture of the thing itself. Fritz Zwicky died in 1974, just as the rotation curve evidence was beginning to pile up. He lived long enough to see his missing mass problem taken seriously, but not long enough to see it become the foundation of modern cosmology. Vera Rubin lived until 2016. By the time she passed, dark matter had become one of the biggest unsolved problems in physics. Thousands of scientists were searching for it in underground detectors, particle colliders, and satellite observatories. Entire careers were being built around the search for whatever it is that fills the space between the stars. And still, no one has found it. Not directly, not in a lab. The rotation curves are still flat. The clusters are still holding together. The gravity is still there, steady and measurable. But the thing producing that gravity remains invisible. We have spent nearly a century staring at the universe and realizing that most of it is hiding in plain sight. The cosmic dance of galaxies, the sweeping spirals and the tightly bound clusters, is choreographed by something we cannot see. The stars move too fast. The gas orbits too quickly. The gravitational pull is too strong. Every observation points to the same conclusion. There is more out there than meets the eye, far more. And whatever it is not just filling the gaps, it is holding the whole structure together. We know it is there because we can see what it does to the things around it. The galaxies spin, the clusters stay bound. And out in the vast stretches of intergalactic space, light itself bends and warps as it passes through regions dense with dark matter. That bending, that gravitational lensing, would become the next major clue in the search to understand what 85% of the universe is actually made of. Light does not lie. That was the assumption. For centuries, astronomers trusted that if light arrived from a distant star or galaxy, it had traveled in a straight line. The path might be long, billions of years long, but it was honest. Point A to point B. No detours, no distortions, no funny business. Light was the one messenger in the cosmos you could trust to deliver the message exactly as sent. Then Albert Einstein published his theory of general relativity in 1915, and that assumption collapsed. Light, it turned out, does not travel in straight lines through the universe. It travels along the curves of space-time itself. And space-time, Einstein showed, is not a flat, empty stage where objects move around like actors on a set. It is a fabric. A flexible, warping, bendable thing that responds to the presence of mass and energy. Put a heavy object in space, and the space around it curves. Light traveling through that curved region follows the curve. From the light's perspective, it is still moving in a straight line. From our perspective, watching from the outside, the light has bent. Einstein predicted this mathematically, but the first real test came in 1919 during a total solar eclipse. A British astronomer named Arthur Eddington traveled to the island of Principe off the coast of West Africa and photographed stars near the edge of the sun during totality. The sun's gravity, Einstein's theory predicted, should bend the light from those stars as it passed by, making them appear slightly shifted from their usual positions. Eddington measured the positions. They were shifted, exactly as Einstein said they would be. The announcement made headlines around the world. Space-time was real. Gravity was not a force pulling objects together. It was the geometry of the universe itself, warped by mass. That discovery opened a door. If the sun could bend light from nearby stars, what could a galaxy do? What about a cluster of galaxies? What about something even heavier? Einstein himself worked through the math in a paper published in 1936. He showed that if a massive object passed directly between Earth and a distant light source, the foreground mass would bend the light around itself in all directions, creating a ring, a perfect circle of distorted light surrounding the lensing object. He called it a gravitational lens. Einstein did not think anyone would ever see one. The alignment would have to be nearly perfect, he argued, and the odds of that happening by chance were absurdly small. He published the paper more as a mathematical curiosity than a prediction. He was wrong about the odds. The universe, it turns out, is large enough and filled with enough galaxies that rare alignments happen all the time. You just have to know where to look. The first gravitational lens was discovered in 1979. Two astronomers, Dennis Walsh and Bob Carswell, were studying what they thought were two separate quasars sitting very close together in the sky. Quasars are the brilliant cores of distant galaxies powered by supermassive black holes. Finding two of them next to each other was unusual but not impossible. Then Walsh and Carswell measured the spectra of both objects. The light signatures were identical. Same redshift, same emission lines, same everything. The odds of two independent quasars having exactly the same spectrum are effectively zero. The only explanation that made sense was that they were looking at one quasar whose light had been split into two images by a massive foreground object, bending the light into two separate paths toward Earth. They were right. Follow-up observations found a faint galaxy sitting almost exactly between the quasar and Earth. The galaxy's gravity was acting as a lens, bending the quasar's light around it and creating a double image. Einstein's ring had shown up, not as a perfect circle because the alignment was slightly off, but as two bright arcs. The effect was real. Gravitational lensing was not a mathematical toy, it was a tool. And it was about to become one of the most powerful methods astronomers had for detecting dark matter. Here is why lensing matters. When light from a distant galaxy passes through a region of space containing a lot of mass, the path of that light bends. The amount of bending depends on how much mass is there, not how much light is being emitted, not how many stars you can count, just mass, total mass. Gravitational lensing does not care whether the mass is glowing or dark. It measures everything. A cluster of galaxies sitting between Earth and a more distant background galaxy will distort the background galaxy's image, sometimes dramatically, stretching it into arcs or splitting it into multiple copies, sometimes subtly, warping its shape just slightly. By analyzing those distortions, astronomers can calculate how much mass the foreground cluster contains and where that mass is distributed. And here is the kicker. When they do that math, the amount of mass required to produce the observed lensing is always far greater than the amount of visible matter in the cluster. Always, by a factor of 5 or 6 or more. The lensing signal points to mass that is not emitting light. Mass that does not show up in any wavelength from radio to gamma rays. Mass that is only detectable because of what it does to space-time itself. NASA calls dark matter the invisible glue that holds the universe together. The University of Chicago describes it as an invisible web extending across the universe, creating a scaffold for all the stars and galaxies. CERN notes that researchers infer dark matter only from the gravitational effect it seems to have on visible matter. Gravitational lensing is the clearest, most direct way to see that effect, not metaphorically, literally. You point a telescope at a distant galaxy. You measure how its image has been stretched or distorted. You calculate how much mass is needed to cause that distortion. Then you count up all the stars and gas you can see in the foreground. The numbers do not match. The missing mass is dark. There are two types of gravitational lensing, and they work at different scales. Strong lensing is the dramatic version. It happens when the alignment between a massive foreground object and a distant background source is very close, and the foreground mass is heavy enough to bend light severely. The result is arcs, rings or multiple images of the background object, all smeared and distorted around the lensing mass. Strong lensing is rare because it requires nearly perfect alignment, but when it happens, the images are unmistakable. The Hubble Space Telescope has captured dozens of stunning examples. Entire galaxies bent into crescents, stretched around the cores of galaxy clusters like light caught in a funhouse mirror. Weak lensing is subtler. It does not create dramatic arcs or rings. Instead, it produces tiny statistical distortions in the shapes of many background galaxies scattered across a wide patch of sky. Each individual distortion is small, often too small to notice by eye. But when you measure the shapes of thousands of galaxies and look for patterns in how they have been stretched or squashed, you can map out where the foreground mass is concentrated. Weak lensing works like a census. You are not looking for one perfect alignment. You are looking for slight shape changes across an entire population. The more galaxies you measure, the more precisely you can reconstruct the invisible mass distribution that caused those changes. Both methods point to the same conclusion. There is far more mass in the universe than we can see, and that mass is not randomly scattered. It is organized, concentrated in halos around galaxies, piled up in massive clumps at the centers of galaxy clusters, spread out in vast filaments connecting clusters across hundreds of millions of light years. The gravitational lensing maps trace a skeleton, a hidden architecture that holds the visible universe together. The bullet cluster is the case that made this undeniable. It sits roughly 3.7 billion light-years from Earth, and it is actually two galaxy clusters that collided with each other about 150 million years ago. When galaxy clusters collide, the galaxies themselves mostly pass through each other. Galaxies are mostly empty space. Stars are tiny, and the distances between them are enormous. The odds of two stars actually hitting each other during a galactic collision are vanishingly small, but the hot gas filling the space between galaxies does not pass through cleanly. Gas is thicker. When two clouds of gas slam into each other at millions of kilometers per hour, they collide, heat up, and slow down. That collision creates a shock wave, a region of superheated gas glowing brightly in X-rays. The bullet cluster got its name because one of the colliding clusters punched through the other, leaving a bullet-shaped shockwave of hot gas trailing behind it. Astronomers can see that gas clearly in X-ray images. It is bright, well-defined, and sitting exactly where you would expect it to be if two clouds of ordinary matter had crashed into each other and stalled. The galaxies themselves, the stars and the dark matter halos surrounding them, kept moving. They passed through the collision relatively unaffected. Now here is the critical part. Astronomers used gravitational lensing to map where the total mass in the bullet cluster actually is. They measured the distortions in the shapes of hundreds of background galaxies and reconstructed the mass distribution. What they found was stunning. The bulk of the mass, the regions where space-time is most severely curved, is not sitting where the hot gas is. It is sitting where the galaxies are. The visible stars make up only a tiny fraction of that mass. The rest, the vast majority, is dark matter, invisible, collisionless, unaffected by the crash. The dark matter passed straight through the collision zone along with the galaxies, while the ordinary matter, the gas, got stuck in the middle. The bullet cluster is widely described as direct evidence for dark matter's separation from normal matter because the gravitational lensing signal does not line up with the X-ray emitting baryonic gas. You have two maps. One shows where the ordinary matter is. The other shows where the gravity is strongest. They do not match. The gravity, the thing doing the lensing, is coming from regions dominated by dark matter. If dark matter did not exist, if all the mass in the cluster were ordinary matter, the two maps would overlap. They do not. The lensing map and the X-ray map tell completely different stories, and the only way to reconcile those stories is to accept that most of the mass in the cluster is something that does not emit light, does not absorb light, and did not slow down when the gas clouds collided. The bullet cluster was not the first lensing observation to point toward dark matter, but it was the cleanest. The separation between the dark matter and the ordinary matter is so stark, the lensing signal so strong, that it became the poster child for dark matter evidence. Researchers at the time called it a smoking gun. Some still do. It is hard to look at the bullet cluster data and argue that dark matter is an illusion or a mistake in the equations. The mass is there. The lensing proves it. The mass is not where the visible matter is. The X-rays prove that. Whatever is bending the light is not ordinary. Gravitational lensing does more than just confirm dark matter exists. It lets astronomers weigh things. You can point a telescope at a galaxy cluster, measure the lensing, and calculate the total mass of the cluster without ever identifying a single star. You can map the three-dimensional shape of dark matter halos around galaxies by analyzing how they distort the light from galaxies behind them. You can trace the distribution of dark matter across enormous stretches of the universe by measuring weak lensing in deep sky surveys covering millions of galaxies. This is not guesswork. This is geometry. Light bends by a specific amount, depending on how much mass it passes by and how close it gets. Measure the bending, and you know the mass. The math is solid, the predictions are testable. And every time astronomers run the test, they find more mass than they can account for with stars, gas, planets, black holes, or any form of ordinary matter. The missing mass is always there, invisible and silent, detectable only by the way it warps the fabric of space-time. One subtle but important detail. Gravitational lensing measures total mass, not dark matter alone. The lensing signal includes everything: stars, gas, dust, black holes, dark matter, all of it. To figure out how much of that mass is dark, astronomers have to subtract the contribution from visible matter. They count the stars, measure the gas, estimate the black holes, add it all up, and compare it to the total mass inferred from lensing. The difference is dark matter. In every case, the dark matter dominates. Visible matter makes up about 15% of the total. The other 85% is dark. That number, 85%, shows up everywhere. Galaxy clusters, individual galaxies, the large-scale structure of the universe. Everywhere astronomers look, the ratio holds. Dark matter outweighs visible matter by a factor of 5 or 6 to 1. The universe, at the level of matter, is built mostly out of something we cannot see. Gravitational lensing is how we know that. It is the cosmic scale that lets us weigh the invisible. The James Webb Space Telescope has started pushing lensing observations even further. Webb's infrared sensitivity allows it to detect extremely faint, distant galaxies that Hubble could barely see. Many of those galaxies sit behind massive foreground clusters that act as natural telescopes, their gravity magnifying the light from the distant objects. By studying how those background galaxies are lensed, astronomers can measure the mass distribution of the foreground clusters in extraordinary detail. Some of the lensing maps produced by Webb are so precise that researchers can identify individual clumps of dark matter within galaxy clusters, tracing structure on scales much smaller than was possible before. And here is where it gets strange. The lensing maps show structure everywhere. Dark matter is not a smooth, featureless fog filling the space between galaxies. It is clumpy, filamentary, organized into halos and subhalos and streams. It looks, in the maps, like a web. A vast, interconnected network of dark matter filaments stretching across hundreds of millions of light-years, with galaxy clusters sitting at the nodes where multiple filaments intersect. The visible galaxies, the stars we see, are embedded in that web like lights strung along a scaffold. The scaffold itself is invisible, but the lensing maps reveal it in exquisite detail. The cosmic web, as astronomers call it, is not a metaphor. It is a real structure traced by gravitational lensing and confirmed by galaxy surveys and computer simulations. Dark matter collapsed into filaments and halos in the early universe, pulled together by its own gravity. Ordinary matter, the gas that would eventually form stars, followed the dark matter into those halos. Galaxies formed where the dark matter was densest. The entire visible universe, every star and planet and nebula, is built on top of a foundation made of something we cannot see and do not understand. Gravitational lensing is the tool that made that foundation visible, not directly, but through its effects. Mass bends light. Dark matter is mass. Bend enough light, and you can map the dark. That is what lensing does. It turns the invisible into something measurable, not observable in the traditional sense. You still cannot take a picture of dark matter, but you can take a picture of what dark matter does to the light passing through it. And from that, you can reconstruct where the dark matter must be. Fritz Zwicky inferred missing mass in 1933 from the motions of galaxies in the Coma cluster. Vera Rubin measured flat rotation curves in spiral galaxies in the 1970s. Both were indirect measurements. Both relied on the assumption that gravity behaves the way Einstein said it does. Gravitational lensing is different. It does not rely on assumptions about how galaxies move or how stars orbit. It is a direct consequence of general relativity. Light follows space-time. Space-time curves around mass. Measure the curve, and you measure the mass. The measurement does not depend on what the mass is made of, or whether it glows, or how old it is. It just depends on how much of it there is. That is why lensing has become the gold standard for dark matter evidence. It is harder to dismiss than rotation curves or velocity dispersions because the effect is so direct. The light is bent. That bending requires mass. The mass is not visible, therefore the mass is dark. The logic is airtight, and the observations back it up. Every deep lensing survey, every cluster study, every weak lensing map of large-scale structure, they all point to the same thing. The universe contains far more matter than we can see, and that matter is distributed in ways that match the predictions of dark matter models almost perfectly. The invisible hand Einstein described is everywhere. It holds galaxies together, it binds clusters, it shapes the cosmic web, and it bends light. That bending is the signature, the one way dark matter announces its presence without emitting a single photon. For decades, astronomers have been reading that signature, refining the measurements, sharpening the maps. And every new observation confirms what Zwicky suspected nearly a century ago. Most of the universe is missing, not because it is not there, but because it refuses to shine. We know it is there because of what it does to the things we can see. The stars move too fast, the clusters hold together, and the light, traveling across billions of years of space, arrives at our telescopes bent and stretched and distorted by the gravity of something that will never show up in any picture. Gravitational lensing is not proof that we understand what dark matter is. It is proof that it exists. The rest, the what and the why and the how, is still waiting for an answer. And that answer, whatever it turns out to be, will have to explain why 85% of all the matter in the universe has spent the last 14 billion years hiding in plain sight. We know dark matter is there. The galaxies spin too fast. The clusters hold together. The light bends. Every observation points to the same conclusion. Most of the matter in the universe is invisible, 85% of it. That is not a small discrepancy. That is not a rounding error. That is the vast majority of the material holding the cosmos together, refusing to show up in any telescope humanity has ever built. So what is it? That question has a surprisingly short list of possible answers, and the process of narrowing down that list has taken decades of careful elimination. The first instinct, the most natural assumption, was that dark matter is just ordinary matter that happens to be dark. Regular atoms, protons and neutrons and electrons, the same stuff that makes up stars and planets and human bodies, just not glowing, not emitting light, not reflecting light. Sitting quietly in the dark, doing nothing but exerting gravity. There are plenty of objects in the universe that fit that description. Dead stars, brown dwarfs, rogue planets, black holes, clouds of cold molecular gas drifting through intergalactic space. All of these things are made of ordinary matter, and all of them are extremely hard to detect unless they happen to pass in front of something brighter. Collectively, astronomers gave them a name, MACOS, Massive Astrophysical Compact Halo Objects. The acronym was a deliberate jab at the other leading candidate at the time, WIMPs, which we will get to in a moment. The macho hypothesis was straightforward. Maybe the missing mass in galaxies is not exotic particles from beyond the standard model of physics. Maybe it is just a huge population of dim, heavy objects scattered throughout galactic halos. Objects too faint to see individually, but collectively massive enough to explain the flat rotation curves and the gravitational lensing. It was a reasonable idea. It did not require inventing new physics. It did not demand the existence of particles that had never been detected. It just required a lot of stuff that was hard to see. The problem was proving it. If machos exist in large numbers, they should occasionally pass in front of distant stars and cause a brief brightening as their gravity lenses the starlight. The effect is called gravitational microlensing, and it is detectable if you monitor enough stars for long enough. In the 1990s, 2 major observational campaigns were launched to do exactly that. One was called Macho, naturally. The other was called EROS, the Experience pour la recherche d'objets sombres. Both teams monitored millions of stars in the Large Magellanic Cloud and the galactic bulge, looking for the telltale flicker of a macho passing by. They found some, not zero. A handful of microlensing events were detected, confirming that there are dark compact objects out there. Brown dwarfs, probably. Maybe some rogue planets. The numbers, however, did not add up. The frequency of microlensing events was far too low to account for the amount of dark matter needed to explain galaxy rotation curves. If machos were responsible for most of the missing mass, the surveys should have detected hundreds or thousands of events. They found a few dozen. The conclusion was unavoidable. Machos exist, but they are not the answer. They make up a small fraction of the dark matter at best. The bulk of it has to be something else. That something else cannot be ordinary matter. And here is where the cosmology gets uncomfortable. Ordinary matter, the kind made of protons and neutrons and electrons, has a technical name in physics: baryonic matter. Baryons are particles made of 3 quarks. Protons and neutrons are baryons. Electrons are not, but they are always lumped in with baryonic matter because they hang around with protons and neutrons to form atoms. When cosmologists talk about baryonic matter, they mean everything in the periodic table: hydrogen, helium, carbon, oxygen, iron, all of it. The stuff that stars are made of, the stuff that planets are made of, the stuff you are made of. The amount of baryonic matter in the universe is not a guess. It is constrained by observations of the cosmic microwave background and by measurements of element abundances left over from the first few minutes after the Big Bang. During that brief window, when the universe was hot enough for nuclear fusion to occur everywhere at once, protons and neutrons fused into helium and trace amounts of lithium and deuterium. The ratios of those elements depend very sensitively on how many baryons were present. Measure the ratios today, and you can calculate how much baryonic matter existed back then. The answer is about 5% of the total mass energy budget of the universe. 5%. That includes every star, every planet, every gas cloud, every black hole, everything made of atoms. All of it adds up to 5%. Dark matter, by contrast, makes up roughly 27% of the universe. That is more than 5 times as much mass as all the ordinary matter combined. And the kicker is that dark matter cannot be baryonic. If it were, the element ratios from the Big Bang would be completely different. There would be more helium or less deuterium, or the cosmic microwave background would have a different structure. The numbers do not allow it. Whatever dark matter is, it is not made of protons and neutrons. It is not on the periodic table. It is something else entirely. That realization, which solidified in the late 1990s and early 2000s, forced physicists to confront an uncomfortable truth. The standard model of particle physics, the enormously successful framework that describes all known particles and forces, does not include dark matter, not even a little bit. The standard model has quarks and leptons, which make up matter. It has bosons, which carry forces. It has the Higgs boson, which gives particles mass. It has been tested to absurd precision at particle colliders around the world, and it works beautifully. Every prediction it makes has been confirmed. Every particle it predicted has been found, culminating in the discovery of the Higgs at CERN in 2012. And yet, the standard model cannot explain 85% of the matter in the universe. That is not a minor gap. That is not a detail to be worked out later. That is a gaping hole in the foundation of modern physics. The universe, observationally, contains far more matter than the Standard Model allows for. Either the Standard Model is incomplete or our understanding of gravity is wrong. Most physicists bet on the former. Gravity has been tested extensively, and general relativity works at every scale we have been able to measure, from GPS satellites to black hole mergers to the bending of light around galaxy clusters. Modifying gravity to eliminate the need for dark matter has been tried repeatedly, and none of the proposed modifications fit all the data. Dark matter fits. It fits the rotation curves, the lensing, the large-scale structure, the cosmic microwave background. It fits everything. The problem is, we do not know what it is. The leading candidate for a long time was a class of particles called WIMPs, weakly interacting massive particles. The name is technically accurate, though it was also chosen because it made for a great acronym pairing with machos. WIMPs are hypothetical particles that interact via gravity and possibly the weak nuclear force, but not via electromagnetism. That last part is critical. Electromagnetism is the force responsible for light. If a particle does not interact electromagnetically, it does not emit light, does not absorb light, does not reflect light. It is invisible. A WIMP passing through your body right now, and trillions of them probably are, would sail straight through without interacting with a single atom. You would never feel it. Your atoms would never notice. WIMPs are attractive as a dark matter candidate for several reasons. First, they naturally fall out of certain extensions to the Standard Model. Supersymmetry, one of the most popular proposed extensions, predicts a whole zoo of new particles, many of which would be stable, massive, and weakly interacting. The lightest of these particles, called the neutralino, fits the WIMP profile almost perfectly. It would have been produced in vast quantities in the early universe, and it would have survived to the present day because it does not decay into anything lighter. It would clump around galaxies under the influence of gravity, forming the halos that Vera Rubin's rotation curves pointed to, and it would be completely invisible to every telescope ever built. Second, WIMPs have a convenient property called thermal relic abundance. In the first moments after the Big Bang, the universe was a hot, dense soup of particles colliding and annihilating and being created out of pure energy. As the universe expanded and cooled, heavier particles stopped being produced because there was not enough energy left to make them. The ones that already existed either decayed or annihilated with their antiparticles. WIMPs, if they exist, would have been created in enormous numbers in the early universe. Most of them would have annihilated when they collided with other WIMPs, but as the universe expanded and the density dropped, those collisions became rarer. Eventually, the annihilation rate dropped below the expansion rate, and the remaining WIMPs froze out. They stopped annihilating, they just drifted. The remarkable thing is that if you run the numbers, the predicted abundance of WIMPs left over from the Big Bang matches almost exactly the observed abundance of dark matter today. That is not a small coincidence. It is a numerical hint that WIMPs might be real. Physicists call it the WIMP miracle. The math just works. Plug in reasonable values for the WIMP mass and interaction strength, and out pops the right amount of dark matter. That kind of agreement does not happen by accident. It suggests that WIMPs, or something very much like them, might actually be what dark matter is made of. The problem is that no one has ever detected a WIMP, not in a particle collider, not in an underground detector, not anywhere. And it is not for lack of trying. For more than 3 decades, physicists have been building increasingly sensitive experiments designed to catch WIMPs in the act of interacting with ordinary matter. The expectation is that even though WIMPs interact very weakly, they should occasionally bump into an atomic nucleus as they pass through a detector. That collision would deposit a tiny amount of energy, maybe enough to cause a flash of light or a small vibration in a crystal. Detect that signal, rule out every possible background source, and you have found your WIMP. Dozens of experiments have been built. They sit deep underground, shielded from cosmic rays by kilometers of rock. They use ultra-pure materials to minimize radioactive contamination. They cool their detectors to near absolute zero to reduce thermal noise. They monitor every signal with exquisite precision, looking for the faint whisper of a dark matter particle interacting with their target material. And so far, they have found nothing. No confirmed WIMP detections. No clear signal rising above the background. A few experiments have reported tantalizing hints over the years, small excesses in their data that could possibly be dark matter. None of those hints have held up under further scrutiny. The null results have piled up. The parameter space where WIMPs could be hiding has shrunk. That does not mean WIMPs do not exist. It just means that if they do exist, they interact even more weakly than the simplest models predicted. Or they are heavier, or lighter, or their properties are such that current detectors are not sensitive to them. The search is not over. New experiments are being built with even greater sensitivity. But the WIMP hypothesis, once the overwhelming favorite, has lost some of its shine. The WIMP miracle is still a miracle, but the lack of detection is starting to feel less like bad luck and more like a hint that the answer might lie elsewhere. And here is the deeper problem. Identifying a particle that does not interact electromagnetically is extraordinarily difficult. Electromagnetism is how we detect almost everything. Telescopes collect light, particle detectors measure electric charge. Even neutral particles like neutrons are detected indirectly through their interactions with charged particles. A particle that refuses to interact electromagnetically at all is nearly invisible by design. The only handle you have on it is gravity, and gravity is the weakest force in nature, by an absurd margin. The electromagnetic force between two protons is roughly 10 to the 36 times stronger than the gravitational force between them. That is a 1 followed by 36 zeros. Detecting something purely through its gravitational influence when you are trying to study individual particles is almost impossibly hard. That is why dark matter remained hidden for so long. It does not light up. It does not leave trails in detectors. It does not collide with ordinary matter in any way that produces a clear signal. It just sits there, invisible and silent, pulling on things with gravity. The only reason we know it exists at all is because we can measure the gravity at cosmic scales, galaxies, clusters, lensing, the large-scale structure of the universe. All of those observations involve enormous amounts of mass spread over vast distances. The gravitational effects add up. But when you try to catch a single dark matter particle in a lab, the gravitational pull is negligible. You need the particle to interact some other way, and if it does not, you are stuck. This is the 85% conundrum. We know dark matter exists. The evidence is overwhelming. We know it is not ordinary matter. The Big Bang nuclear synthesis numbers and the microlensing surveys rule that out. We know it has to be some kind of particle, or possibly multiple kinds of particles, that interacts via gravity and maybe via some other force we have not identified yet. We have reasonable theoretical candidates. WIMPs are one, axions are another, sterile neutrinos are a third. Each has its own theoretical motivation and its own set of predicted properties. And each is maddeningly difficult to detect because the one thing they all have in common is that they do not interact with light. NASA calls dark matter the invisible glue that holds the universe together. The University of Chicago describes it as an invisible poltergeist, known only by the effects it has on visible matter. CERN notes that researchers infer dark matter solely from the gravitational effect it seems to have on visible matter. These are not poetic flourishes. These are the most accurate descriptions available. Dark matter is a thing we cannot see, made of particles we have never detected, interacting through forces we do not fully understand, and it makes up 85% of the matter in the universe. That number is staggering. 85%. Imagine walking into a library where 85% of the books are invisible. The shelves are there. You can see the structure of the library, the organization, the way the books are arranged, but you cannot read the spines. You cannot pull the books off the shelves. You cannot even confirm that they are books rather than, say, blocks of wood or empty boxes. All you know is that something is there because the shelves are bending under the weight. That is where we are with dark matter. We can see the structure it creates. We can measure its effects. We just cannot touch it. The standard model of particle physics is one of the most successful theories in the history of science. It describes the behavior of every known particle with stunning precision. It predicted the existence of the W and Z bosons, the top quark, and the Higgs boson, all of which were later discovered exactly where the theory said they would be. The experiments confirming the standard model have been done at energies ranging from room temperature to the hellish conditions inside particle colliders. The theory works, and yet it is incomplete. It has to be, because the standard model has no room for dark matter. There is no particle in the standard model that fits the profile. No particle that is stable, massive, electrically neutral, and abundant enough to make up 85% of the matter in the universe. That gap has physicists in an uncomfortable position. On one hand, they trust the standard model because it has been tested so thoroughly. On the other hand, they know it cannot be the whole story because the universe clearly contains things the standard model does not describe. Dark matter is the most obvious example. Dark energy, the mysterious force accelerating the expansion of the universe, is another. Neutrino masses, which were only recently confirmed, required an extension to the standard model as well. The theory is not wrong, it is just incomplete. And figuring out what lies beyond it is one of the central challenges of modern physics. WIMPs were supposed to be the answer. They fit the data. They emerged naturally from supersymmetry, a well-motivated extension to the standard model. They explained the thermal relic abundance. They were detectable, at least in principle. For decades, they were the leading candidate. But as the searches came up empty and the null results piled up, the confidence in WIMPs began to erode. Not because the theory is bad, but because the universe has not cooperated. The particle, if it exists, is hiding better than anyone expected. That leaves the field in a strange state. We know dark matter is real. We know it is not baryonic. We know it does not interact electromagnetically. Beyond that, we are guessing. The guesses are educated, grounded in solid theoretical reasoning, and backed by decades of observation. But they are still guesses. The 85% conundrum is not a failure of observation. We have observed dark matter's effects in extraordinary detail. It is a failure of identification. We cannot point to a particle and say, that is it. That is what dark matter is made of. The search has moved underground, literally. The next generation of dark matter detectors are buried deep beneath mountains, shielded from cosmic rays and background radiation, waiting in the dark for the faint whisper of a particle that refuses to be seen. Those experiments, and the physicists running them, are chasing one of the biggest mysteries in science. A mystery that makes up most of the universe. A mystery that holds galaxies together. A mystery that, after nearly a century of searching, still has not revealed its face. The problem with dark matter is that if you want to catch it, you have to go somewhere quiet. Not quiet in the sense of turning down the music or finding a peaceful park bench. Quiet in the sense of a mile underground, surrounded by solid rock, sealed inside a chamber cooled to near absolute zero, where the only thing allowed to move is the rare whisper of a particle that might not even exist. Because dark matter, if it is going to announce itself at all, is going to do so in the faintest possible way. A single collision, a tiny recoil, a flash of light, or a vibration so small that every other source of noise in the universe has to be eliminated just to have a chance of seeing it. This is not metaphorical. The experiments hunting for dark matter particles are some of the quietest places on Earth. They have to be. Because the signal they are looking for is buried under an avalanche of background radiation that would drown it out completely if you tried to run the experiment on the surface. Cosmic rays, the high-energy particles raining down from space, hit the Earth constantly, millions of them every second. Each one carries enough energy to trigger a detector, creating a false signal that looks exactly like what a dark matter particle might produce. Run your detector on the surface, and you would be swamped, buried under so much noise that you would never see the real event, even if it happened right in front of you. So the detectors go underground, deep underground, not just a basement, not just a mine shaft, miles below the surface, where the weight of the rock overhead filters out nearly all of the cosmic rays. A cosmic ray particle trying to reach a detector buried under a kilometer of stone has to punch through enough matter that most of them do not make it. The ones that do are rare enough that you can start to pick out other signals, fainter ones. The kind that might come from a dark matter particle drifting through your detector and nudging an atomic nucleus just hard enough to notice. The strategy is called direct detection. The idea is simple in principle. Fill a tank with some material, usually a noble liquid like xenon or argon, and wait. Dark matter particles are thought to be streaming through the Earth constantly, trillions of them passing through every square centimeter every second. Most of them sail straight through without interacting with anything. But once in a very great while, one might collide with an atomic nucleus in your detector. That collision would transfer a tiny amount of energy to the nucleus, causing it to recoil. The recoil would produce a flash of light or a small electrical signal. Detect that signal, confirm that it is not from any known background source, and you have found dark matter. One particle at a time. That is the theory. The practice has turned out to be monstrously difficult. The first problem is location. If you are going to build a detector sensitive enough to catch a dark matter particle, you need to put it somewhere the cosmic rays cannot reach. The best locations are deep underground in facilities originally built for other purposes, old mines mostly. Mines that went deep enough to be useful and were stable enough to be converted into laboratories. SNOLAB in Canada is one. It sits more than 2 kilometers underground in an active nickel mine near Sudbury, Ontario. The rock overhead is thick enough to reduce the cosmic ray flux by a factor of about 10 million. That is not an exaggeration. On the surface, cosmic rays hit at a rate of thousands per square meter per second. At SNOLAB, the rate drops to a few per square meter per day. That reduction is critical. Without it, the experiment would be blind. Gran Sasso in Italy is another. The lab sits under the Gran Sasso mountain in the Apennines, accessed by a tunnel originally built for highway traffic. The rock overhead provides about the same level of shielding as SNOLAB. Several major dark matter experiments have been housed there over the years, along with experiments studying neutrinos and other rare processes. The location is not chosen for convenience. It is chosen because the mountain itself acts as a filter, blocking the noise so the signal has a chance to emerge. Even with that shielding, cosmic rays are not the only problem. Radioactive decay is everywhere. The rocks surrounding the lab contain trace amounts of uranium and thorium. Those elements decay, releasing gamma rays and neutrons. The detector itself, no matter how carefully it is constructed, contains trace radioactive contaminants, the steel in the walls, the glass in the sensors, the solder holding the electronics together. Every material on Earth contains tiny amounts of radioactive isotopes, and every decay event produces a signal that could be mistaken for dark matter. The experiments go to absurd lengths to minimize this. Ultra-pure materials, custom fabricated components with radioactivity levels measured in parts per trillion, shielding layers made of lead and copper and polyethylene stacked around the detector core to block external radiation, and still the background is there, faint but present. The job of the experimentalists is to measure that background, understand it, model it, and subtract it from the data. What is left, if anything, might be dark matter. The detectors themselves are marvels of engineering. Take Lux Zeppelin, or LZ, one of the leading experiments currently running. It sits nearly a mile underground at the Sanford Underground Research Facility in South Dakota, housed in a cavern carved out of rock that used to be part of the Homestake gold mine. The detector core is a tank holding about 10 tons of liquid xenon. Xenon is an inert noble gas, but when you cool it to -95 degrees Celsius, it becomes a liquid. That liquid is extraordinarily pure. Any impurities would absorb the faint light signals the experiment is trying to detect. So the xenon has been filtered and purified to remove contaminants down to parts per trillion. The idea behind LZ and other xenon-based detectors is that when a dark matter particle collides with a xenon nucleus, the recoiling nucleus produces two signals. First, a flash of ultraviolet light as electrons in nearby xenon atoms get excited and then relax. Second, a burst of ionization as electrons are knocked free from atoms along the recoil path. Those free electrons drift upward through the liquid xenon under the influence of an electric field and eventually cross into a layer of gaseous xenon at the top of the tank, where they produce a second flash of light. By measuring both signals, the timing, the brightness, and the position, experimentalists can reconstruct where the event happened, how much energy was deposited, and whether the event looks like a nuclear recoil or some other kind of interaction. Nuclear recoils are the signature of dark matter. Other interactions, like gamma rays scattering off electrons, produce a different pattern and can be rejected. The LZ detector is surrounded by layers of shielding, water tanks, lead bricks, polyethylene panels. Each layer blocks a different kind of background radiation. The whole apparatus sits inside a clean room to prevent dust and other contaminants from drifting in. The detectors monitoring the xenon are mounted on frames made of ultra-low radioactivity titanium. The cables are custom. The sensors are custom. Even the air in the room is filtered. Every component has been screened for radioactive contamination before it was allowed anywhere near the experiment. And the results, so far, are null. LZ has been running for several years. It has collected an enormous amount of data. It has achieved some of the lowest background rates ever recorded in a dark matter detector. It has ruled out large swaths of parameter space where WIMPs might have been hiding. It has not detected a WIMP, not one. The tank has been sitting there, quiet and cold and exquisitely sensitive, and the dark matter particles, if they are passing through, have declined to introduce themselves. That is not a failure. That is how science works. Null results are still results. Every experiment that comes up empty narrows the search. It tells you where dark matter is not, or at least where it is not in the form you were looking for. LZ and experiments like it have pushed the sensitivity of direct detection down by orders of magnitude over the past 2 decades. They are now sensitive enough to detect interactions so rare that they happen less than once per ton of detector material per year. That level of sensitivity is extraordinary. It is also increasingly running into a new problem: neutrinos. Neutrinos are a type of fundamental particle that interacts very weakly with matter. They are produced in enormous numbers by the sun, by cosmic rays, by radioactive decay, and by a dozen other processes scattered across the universe. Trillions of neutrinos pass through your body every second. You do not notice because they almost never interact with anything. Almost never is not the same as never. Every so often, a neutrino will collide with an atomic nucleus, causing it to recoil. That recoil looks exactly like the recoil a dark matter particle would produce. Same energy range, same interaction signature, indistinguishable. For decades, this was not a problem because dark matter detectors were not sensitive enough to see neutrino interactions. The event rate was too low, and the detectors had bigger backgrounds to worry about. But as the experiments got better, as the backgrounds were reduced and the sensitivity improved, neutrinos started showing up. In late 2025, LZ reported the first detection of solar neutrinos via a process called coherent elastic neutrino nuclear scattering. This was a major achievement in neutrino physics. It confirmed a prediction that had been made decades earlier. It also marked a turning point for dark matter searches because it means the experiments are now sensitive enough to see the neutrino background, and that background is irreducible. You cannot shield against it. Neutrinos pass through a mile of rock as easily as they pass through air. They are always there. This is what physicists call the neutrino floor. The point at which dark matter detectors become sensitive enough that neutrinos start producing events at a rate comparable to or higher than the expected dark matter signal. Once you hit that floor, it becomes much harder to claim a discovery. If you see an event, how do you know it was dark matter and not a neutrino? The answer is you probably cannot, not from a single event. You would need to see many events and look for statistical patterns that distinguish dark matter from neutrinos. Dark matter, for example, should produce a signal that varies with the Earth's motion through the dark matter halo. Neutrinos from the sun should track the sun's position in the sky. With enough events, you might be able to separate the two. But that requires even larger detectors, even longer run times, and even more sophisticated analysis. The scale of these experiments is increasing. LZ uses 10 tons of xenon. The next generation detector being planned, called XLZD, is expected to use closer to 50 tons. Other experiments are using different target materials to probe different parts of the WIMP parameter space. Xenon, another leading experiment, also uses liquid xenon and sits in the Gran Sasso lab in Italy. PICO, a detector based in Canada, uses a different technology entirely. Instead of a liquid noble gas, PICO uses superheated liquids, fluids held just below their boiling point. When a particle interacts with the liquid, it deposits enough energy to create a tiny bubble. The bubble grows, and its formation is detected acoustically. The advantage of this approach is that it is less sensitive to certain backgrounds, particularly electron recoils, which makes it good for searching for specific types of dark matter interactions. The disadvantage is that it is harder to scale up to very large volumes. Each experiment has its strengths, each has its blind spots. The field has diversified because no single detector technology is perfect. WIMPs, if they exist, could interact in different ways depending on their mass and their coupling to ordinary matter. A detector optimized for light WIMPs might miss heavy ones. A detector sensitive to spin-dependent interactions might not see spin-independent ones. So the strategy has been to build multiple experiments using different techniques and compare results. If several independent experiments all see the same signal, confidence goes up. If they all see nothing, the null result is more robust. The scale of the engineering behind these detectors is staggering. Consider the shielding alone. A typical dark matter experiment is wrapped in layers of material designed to block specific types of radiation. Water is a good neutron moderator, so water tanks surround the detector. Lead blocks gamma rays, so lead bricks are stacked around the core. But lead itself can be radioactive, so the lead has to be ancient lead, salvaged from old structures or shipwrecks where the radioactive isotopes have already decayed. Polyethylene blocks neutrons, so thick sheets of polyethylene are layered outside the lead. Even the air in the detector hall is a concern, because radon, a radioactive gas, can seep out of the rocks and drift into the detector, so the air is continuously filtered and flushed. The xenon itself has to be purified constantly. Even after the initial cleaning, trace contaminants can build up over time. Electronegative impurities, molecules that like to grab onto free electrons, are particularly problematic because they reduce the charge signal. The xenon is continuously circulated through purification systems that remove these impurities. The circulation has to be done carefully because any turbulence or temperature fluctuation can introduce noise into the detector. The entire system is monitored continuously. Temperatures, pressures, flow rates, all of it tracked and logged. If something goes wrong, if a pump fails or a seal leaks or a sensor drifts, the detector has to be shut down, the problem fixed, and the system brought back online. These are not experiments you can run casually. The people running them are patient. They have to be. Dark matter direct detection is not a field where results come quickly. An experiment might take 5 or 10 years to design and build, another 2 or 3 years to commission and debug, then several more years of data taking before you have enough statistics to say anything definitive. And at the end of all that, the most likely outcome is a null result. No WIMP detected, no discovery, just a tighter constraint on where dark matter might be hiding. That is not the kind of work that attracts people looking for quick wins. It attracts people who are comfortable with uncertainty, who can spend a decade chasing a particle that might not exist in the form they are searching for, and who find satisfaction in the process itself rather than the result. There is a certain irony to the whole enterprise. Dark matter is everywhere. It is holding galaxies together. It is the invisible scaffold supporting the cosmic web. It is streaming through your body right now at a rate of trillions of particles per second. And yet when you try to catch one, when you build a detector specifically designed to see a single dark matter particle interacting with a single nucleus, you come up empty. The universe is full of the stuff, but it refuses to be pinned down. It drifts through matter like a ghost, interacting so rarely that even with the most sensitive instruments humanity has ever built, parked in the quietest locations on Earth, shielded from every known source of background radiation, the signal remains maddeningly elusive. The null results are piling up. LZ has ruled out WIMPs over a broad range of masses and interaction strengths. Xenon has done the same. Pandarex, a detector in China, has published similar limits. Each experiment pushes the boundaries a little further. Each one carves out another chunk of parameter space where WIMPs cannot be. And each one leaves the field in a slightly more uncomfortable position because the most natural regions, the places where WIMPs were expected to be, have now been thoroughly searched. If WIMPs exist, they are either heavier or lighter than the original models predicted, or they interact more weakly, or they interact through some channel the current detectors are not sensitive to. That last possibility is taken seriously. The experiments so far have focused primarily on one type of interaction, the scattering of a WIMP off a nucleus via the weak nuclear force. But there are other possibilities. WIMPs could interact with electrons instead of nuclei. They could scatter inelastically, depositing energy in ways the detectors are not optimized to see. They could have additional interactions beyond the standard model weak force. Each alternative opens up new regions of parameter space to explore, and each requires different detector designs or analysis techniques. The field is not giving up, far from it. New experiments are being proposed. Existing experiments are being upgraded. The sensitivity continues to improve. But the easy wins, if there ever were any, are gone. The low-hanging fruit has been picked. What remains is a harder, slower search through increasingly exotic corners of the theoretical landscape, and the neutrino floor is rising. As detectors get better, the neutrino background gets harder to ignore. Eventually, direct detection experiments will reach a point where almost every event they see is a neutrino, and distinguishing dark matter from that background will require statistical methods rather than event-by-event identification. Some physicists argue that we are already there, that the current generation of experiments is butting up against the neutrino floor, and that further progress will require fundamentally different approaches. Others argue that there is still room to improve, that next-generation detectors with better background rejection and more target mass can push through. The debate is ongoing. What is clear is that the straightforward WIMP search, the one that dominated the field for 2 decades, is running into diminishing returns. The particle, if it exists in the form originally envisioned, is hiding better than anyone expected. That does not mean dark matter is not real. The gravitational evidence is overwhelming. Galaxies spin too fast. Clusters hold together. Light bends. The mass is there. But the identity of that mass, the specific particle or particles it is made of, remains unknown. WIMPs were the leading candidate for a long time because they fit the data and because they emerged naturally from extensions to the standard model like supersymmetry. But nature is not obligated to follow our theories. It is entirely possible that dark matter is something else entirely. Something the current generation of detectors is not designed to see. That possibility has opened the door to a much wider range of ideas. Axions, ultra-light particles that would behave more like a wave than a particle. Sterile neutrinos, heavier cousins of the known neutrinos that interact even more weakly. Primordial black holes, tiny dense objects left over from the early universe. Dark photons, hypothetical particles that would mediate a new force between dark matter particles. Each idea has its own theoretical motivation and its own experimental signature, and each requires a different kind of detector. The underground labs, the massive xenon tanks, the ultra-pure materials, all of that infrastructure was built to catch WIMPs. If dark matter is not a WIMP, if it is something lighter or stranger or more exotic, then the search has to move in new directions. Some of those directions involve building new kinds of detectors. Others involve reanalyzing old data with fresh eyes. Still others involve looking for indirect signals, evidence of dark matter particles annihilating in the galactic halo or producing radiation in ways we have not thought to check yet. The search is far from over. It has just gotten harder. The first generation of direct detection experiments set out to catch a particle that everyone expected would show up relatively quickly. It did not. The second generation pushed the sensitivity down by orders of magnitude, expecting the particle to reveal itself in the quieter environment. It still did not. The third generation is now being planned, with even larger detectors and even better background rejection. Maybe those will find it. Or maybe the answer lies somewhere else entirely. Underground, in the cold and the dark and the quiet, the experiments continue, waiting for a signal that might never come, or might arrive tomorrow. The dark matter is out there, somewhere. The detectors are listening, and the silence, so far, has been deafening. The underground detectors have been running for years. The xenon sits there, cold and pure and waiting. The shielding blocks cosmic rays. The sensors watch for the faint flash that would announce a WIMP collision, and nothing happens, or rather, nothing that looks like dark matter happens. Neutrinos show up. Background radiation trickles in despite the miles of rock overhead. But the WIMPs, if they exist, have declined the invitation. The null results keep piling up. And with each passing year, with each new round of data that comes back empty, the field has been forced to admit something uncomfortable. Maybe WIMPs are not the answer. Maybe dark matter is something else entirely. That realization has opened the floodgates. If dark matter is not a weakly interacting massive particle in the 10 to 1000 GeV mass range, then what is it? The theoretical possibilities are vast. Particle physicists have spent decades dreaming up alternatives, each with its own motivation, its own predicted properties, its own experimental signature. Some of these ideas are older than the WIMP hypothesis itself. Others are recent inventions born out of the frustration of not finding what everyone expected to find. What they all have in common is that they predict dark matter behaves differently than WIMPs do, and that means you need different experiments to find them. The leading alternative, the one that has gained the most traction in recent years, is the axion. Axions are not a new idea. They were proposed in 1977 by Roberto Peccei and Helen Quinn, not to explain dark matter, but to solve a completely different problem in particle physics called the strong CP problem. CP stands for charge parity, a symmetry in the laws of physics that says the universe should behave the same way if you swap particles for antiparticles and flip the direction of space. Most forces respect this symmetry. The strong nuclear force, the force that holds quarks together inside protons and neutrons, should violate it. The equations allow for CP violation in the strong force, and yet when physicists measure it, they find nothing, no violation. The strong force respects CP symmetry to an absurd degree of precision, far better than it has any right to. That is the strong CP problem. Why does the strong force respect a symmetry it is allowed to break? Peccei and Quinn proposed a solution. They introduced a new symmetry into the equations, one that would naturally suppress CP violation in the strong force. The symmetry itself is invisible at everyday energies, but it predicts the existence of a new particle. A very light, very weakly interacting particle that would have been produced in enormous quantities in the early universe. Frank Wilczek, one of the physicists who worked out the details, named it the axion after a brand of laundry detergent because, he said, it cleaned up the strong CP problem. The name stuck. For years, axions were just a theoretical curiosity, a particle invented to solve a problem in the equations, with no obvious connection to the real world. Then, in the early 1980s, physicists realized that if axions exist, and if they have the right properties, they could be dark matter. Not all of it, necessarily, but a significant fraction. The math worked. Axions would have been produced in the hot, dense conditions of the early universe through a process that does not require them to be in thermal equilibrium. They would be stable. They would not decay. They would interact so weakly with ordinary matter that they would be effectively invisible, and their predicted abundance, depending on their mass, could match the observed abundance of dark matter almost exactly. That realization transformed axions from a niche idea into one of the leading candidates for what dark matter actually is. The trouble is detecting them. Axions, if they exist, are extraordinarily light. Their mass is expected to be somewhere in the range of 1/1,000,000th of an electron volt to 1,000th of an electron volt. For comparison, an electron weighs about 500,000 electron volts. A proton weighs nearly 1 billion. Axions are so light that calling them particles feels almost misleading. They behave more like waves. A single axion carries almost no energy. But if dark matter is made of axions, there would be trillions of them streaming through every cubic centimeter of space, all moving at roughly the same speed, all oscillating at the same frequency. Collectively, they would form a kind of field, a faint background hum filling the galaxy. The challenge is converting that hum into something detectable. Axions do not interact with ordinary matter directly. They do not collide with nuclei the way WIMPs would. They do not ionize atoms. They do not leave tracks in detectors. What they can do, under the right conditions, is convert into photons, light. If you put an axion inside a strong magnetic field, there is a tiny probability that it will turn into a photon with the same energy as the axion's mass. The probability is absurdly small. But if you have enough axions passing through, and if you tune your detector to exactly the right frequency, you might be able to catch the photons they produce. That is the idea behind ADMX, the Axion Dark Matter Experiment. ADMX is not buried underground. It does not need to be because axions do not get blocked by cosmic rays. It sits at the University of Washington in Seattle, inside a lab that looks more like an electrical engineering workshop than a particle physics experiment. The core of the detector is a cylindrical microwave cavity, a metal can about the size of a trash barrel, sitting inside one of the strongest magnets in the world. The magnet produces a field of about 8 Tesla, roughly 160,000 times stronger than the Earth's magnetic field. The cavity is tuned to resonate at a specific frequency, the frequency corresponding to the energy of the axion mass the experiment is searching for. If an axion passes through the cavity and converts into a photon, and if that photon has exactly the resonant frequency of the cavity, the photon will bounce around inside the cavity, amplifying the signal just enough to be detectable. The detector runs cold, very cold. The cavity is cooled to a few tenths of a degree above absolute zero to reduce thermal noise. At room temperature, the random jiggling of atoms produces enough electromagnetic noise to swamp any signal from axions, cool it down, and the noise drops. The colder you go, the quieter it gets. ADMX operates at temperatures so low that the thermal energy in the cavity is less than the energy of a single axion photon. That is the level of precision required. You are looking for a signal so faint that the ambient heat in the room would drown it out completely. ADMX has been running in various forms since the late 1990s. It has gone through multiple upgrades, each one improving the sensitivity and extending the range of axion masses it can search. In 2018, the experiment hit a major milestone. It achieved sensitivity to what physicists call the classic QCD axion, the version of the axion predicted by the original Peccei-Quinn theory, in a well-motivated mass range around 2 to 4 microelectron volts. That range had been identified decades earlier as the sweet spot where axions are most likely to exist if they are solving the strong CP problem and making up dark matter. ADMX scanned that range. It found nothing, no axion signal, no unexpected photons. The cavity hummed along, quiet and cold, and the axions, if they were there, did not convert. That does not mean axions do not exist. It means they do not exist at that specific mass with that specific interaction strength. Or they do exist, but the local density of axions is lower than expected. Or the experiment missed them for some subtle reason no one has figured out yet. Axion searches are slow. The detector can only scan a narrow range of frequencies at a time. To cover the full range where axions might be hiding, from a millionth of an electron volt up to a thousandth, you would need to run the experiment for decades. ADMX is working its way through the parameter space methodically, frequency by frequency, year by year. Other experiments are doing the same thing using different techniques. Haystack, another axion detector, focuses on higher frequencies. Organ in Australia uses a different cavity design. CAST at CERN looks for axions produced by the Sun rather than axions making up the dark matter halo. Each experiment covers a different piece of the puzzle. Axions have a strange property. If they make up dark matter, they would be moving slowly, at least by particle physics standards. A typical dark matter particle in the Milky Way's halo moves at roughly 200 kilometers per second. That is fast by everyday measures, but in terms of particle energy, it is glacial. The kinetic energy of an axion moving at that speed is far smaller than its rest mass. That means axions in the dark matter halo are non-relativistic. They behave like cold dark matter, clumping under gravity just like WIMPs would. But because they are so light, their quantum mechanical wavelength is enormous. An axion with a mass of a microelectron volt has a wavelength of roughly a meter. That is not a typo. A single axion is spread out over a meter of space. Trillions of them overlap, creating a coherent field that oscillates at a frequency determined by the axion mass. That coherence is what makes axion detection possible. If axions were incoherent, if each one had a random phase, the signals they produced would cancel out. But because the axions in the dark matter halo are all moving at roughly the same speed and were all produced by the same mechanism in the early universe, they are phase-locked. They oscillate together. The detector, if it is tuned correctly, picks up the collective signal from all the axions passing through at once. Not individual particles, but the field they create. It is a fundamentally different kind of search than the one WIMPs require. You are not looking for a collision, you are looking for a resonance. The lack of a WIMP signal has made axions look increasingly attractive. They solve a real problem in particle physics. They naturally emerge from well-motivated theories. They fit the dark matter abundance, and they have not been ruled out yet. The parameter space is large, and most of it remains unsearched. If dark matter is axions, and if their mass falls in the range that experiments like ADMX can reach, we might find them in the next decade or two, or we might not. The search is painstaking, but it is happening. Then there are sterile neutrinos. Neutrinos are a type of fundamental particle that exists in three known varieties called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They are part of the standard model, produced in nuclear reactions, barely interacting with anything. Sterile neutrinos are a hypothetical fourth type. They are called sterile because they do not interact via the weak nuclear force, the force that allows ordinary neutrinos to interact with matter at all. Sterile neutrinos, if they exist, would only interact via gravity and possibly through a tiny mixing with ordinary neutrinos. That makes them incredibly hard to detect, and it makes them a plausible dark matter candidate. The idea is that sterile neutrinos were produced in the early universe, not through collisions and annihilations like WIMPs, but through a process called the Dodelson-Wydrow mechanism, or through resonant production in the presence of lepton asymmetries. The details are technical, but the upshot is that sterile neutrinos could have been created in the right abundance to account for dark matter. Their masses are expected to be in the kilo-electron-volt range, thousands of times heavier than ordinary neutrinos, but still far lighter than WIMPs. That mass range puts them in a category called warm dark matter. Not cold like WIMPs or axions, not hot like ordinary neutrinos, but somewhere in between. Warm dark matter behaves differently than cold dark matter on small scales. Cold dark matter clumps aggressively, forming dense halos and subhalos all the way down to tiny masses. Warm dark matter, because the particles are moving faster, smooths out structure on small scales. It suppresses the formation of the smallest halos. That difference has observable consequences. If dark matter is warm, there should be fewer dwarf galaxies orbiting the Milky Way than cold dark matter predicts. There should be less substructure in galaxy halos. The cores of galaxies might be less dense. Some observations hint that cold dark matter overpredicts small-scale structure, which has made warm dark matter, and sterile neutrinos in particular, an attractive alternative. Other observations suggest cold dark matter is fine, and warm dark matter would smooth things out too much. The jury is still out. Sterile neutrinos have another interesting property. If they exist, and if they have the right mass, they should occasionally decay, not quickly. The lifetime would be longer than the age of the universe. But once in a very great while, a sterile neutrino would split into an ordinary neutrino and an X-ray photon. That X-ray would carry an energy equal to half the sterile neutrino's mass. If dark matter is made of sterile neutrinos, and if they are decaying, there should be a faint X-ray line coming from regions where dark matter is concentrated. Galaxy clusters, the galactic center, dwarf galaxies. Astronomers have looked. They have found some tantalizing hints. A faint X-ray line at about 3.5 kilo electron volts showing up in stacked observations of galaxy clusters. The signal is weak, and it is not clear whether it is real or just a statistical fluctuation. Follow-up observations have been inconclusive. Some see it, some do not. If it is real, it could be sterile neutrinos, or it could be something else entirely. An unidentified atomic transition, instrumental noise, wishful thinking. Sterile neutrinos remain a viable candidate, but they are constrained. The X-ray bounds limit how heavy they can be and how strongly they can mix with ordinary neutrinos. Structure formation limits how light they can be. The allowed parameter space has shrunk over the years, but it has not closed completely. If dark matter is sterile neutrinos, they are hiding in a narrow window, and if they are there, they will be hard to confirm without a clear, reproducible signal. Then there is fuzzy dark matter. The name sounds whimsical, but the idea is serious. Fuzzy dark matter refers to ultralight bosons, particles with masses around 10 to the minus 22 electron volts. That is 20 orders of magnitude lighter than an axion. At that mass, the quantum mechanical wavelength of a single particle is enormous. Not a meter, not a kilometer, thousands of light years. A single fuzzy dark matter particle, if you could isolate one, would be smeared across an entire galaxy. That is not a particle in any traditional sense. It is a wave, a ripple in a field that spans galactic distances. The wave nature of fuzzy dark matter produces effects that are completely unlike anything WIMPs or even axions would do. On large scales, fuzzy dark matter behaves like cold dark matter. It clumps under gravity. It forms halos. It supports galaxies. But on small scales, the wave nature becomes important. The de Broglie wavelength of the particles is so large that they cannot clump into structures smaller than that wavelength. The result is a natural cutoff in the dark matter distribution. Below a certain scale, fuzzy dark matter smooths out. It cannot form tiny, dense halos because the wave interference prevents it. Instead, fuzzy dark matter forms soliton-like cores in galaxy centers. Smooth, stable concentrations of dark matter that do not cusp the way cold dark matter simulations predict. That feature has made fuzzy dark matter appealing because cold dark matter simulations tend to predict that galaxy centers should have steep, cuspy density profiles. Observations of real galaxies, particularly dwarf galaxies, often show flatter cores. The mismatch is called the core cusp problem, and it has been a thorn in the side of cold dark matter for years. Fuzzy dark matter naturally produces cores which could solve the problem, or the problem might not be real. It might be an artifact of how we model galaxy formation, with gas and supernovae and feedback processes that are hard to simulate accurately. Or it might point to something genuinely wrong with cold dark matter. Fuzzy dark matter offers a way out. The challenge with fuzzy dark matter is that it is extraordinarily difficult to detect directly. A particle with a mass of 10 to the minus 22 electron volts has an energy far below anything current detectors can measure. You cannot build a cavity that resonates at that frequency. You cannot cool a detector enough to see individual excitations. The only way to test fuzzy dark matter is through its astrophysical effects. Does it suppress structure on the right scales? Does it produce the right kind of cores? Does it match the observed properties of galaxies and galaxy clusters? The answers are still being worked out. Some simulations suggest fuzzy dark matter fits the data well. Others suggest it creates new problems, like predicting too much structure in the early universe or producing interference patterns in galaxy halos that we do not see. Fuzzy dark matter is part of a broader class of models called ultralight dark matter, spanning masses from about 10 to the minus 24 electron volts up to 10 to the minus 18 electron volts. The exact mass determines the scale at which wave effects become important. Lighter particles have longer wavelengths and suppress structure on larger scales. Heavier particles, closer to the axion mass range, behave more like traditional cold dark matter, except at very small scales. The parameter space is vast, and different parts of it have different observational consequences. Mapping that space is a job for astrophysical observations rather than laboratory experiments. Galaxy surveys, lensing measurements, observations of the cosmic microwave background. Each one constrains a different piece of the ultra-light dark matter puzzle. And then there is the possibility that dark matter is not a single type of particle at all. Maybe it is multiple types. Maybe some of it is WIMPs, some is axions, some is something else. Or maybe dark matter has its own interactions, its own forces, its own sector of physics, completely separate from the standard model. That idea, often called dark sector physics, has gained traction in recent years. The basic notion is that just as ordinary matter interacts via electromagnetism and the weak and strong forces, dark matter might interact via its own set of forces that only dark matter particles feel. A dark photon, for example, would be a hypothetical particle mediating a force between dark matter particles the way ordinary photons mediate the electromagnetic force between charged particles. If dark matter particles interact with each other, even weakly, it changes how they behave. Self-interacting dark matter, as it is called, could scatter off itself as it falls into a galaxy halo, redistributing energy and smoothing out the density profile. That would help with the core-cusped problem. It would also affect how dark matter halos merge and how substructure survives in large halos. The idea has been around for a while, but it has gained attention because it offers a way to tweak cold dark matter just enough to match observations without abandoning the framework entirely. Dark photons and dark sector interactions are hard to test directly because, by definition, they do not couple to ordinary matter except possibly through very weak mixing with standard model particles. The searches for dark photons often look for tiny deviations in particle collision experiments or for anomalous signals in astrophysical data. So far, nothing definitive has turned up, but the parameter space is enormous, and the searches are ongoing. The shift in the field over the past decade has been striking. For years, WIMPs were the default assumption. The experiments were optimized for WIMPs. The theory papers focused on WIMPs. The public talks and press releases centered on WIMPs, and then the detectors came up empty, not all at once. Gradually, over years of data taking and analysis, it became clear that the most natural WIMP parameter space had been searched, and nothing was there. That realization forced the field to broaden. If dark matter is not a WIMP, what else could it be? The answer, it turns out, is a lot of things. Axions, sterile neutrinos, ultralight bosons, dark photons, self-interacting particles, primordial black holes. Each idea has its own theoretical foundation, its own experimental program, its own set of predictions, and each one requires a different way of thinking about what dark matter is and how to find it. The diversity of candidates is both exciting and frustrating. Exciting because it means the field is not stuck. There are new ideas, new experiments, new ways to approach the problem. Frustrating because it means the answer is not obvious. WIMPs were supposed to be the obvious answer. They fit the data. They emerged from well-motivated theory. They were detectable, and they were not there. Or at least, they were not where everyone expected them to be. The lack of a WIMP detection has humbled the field. It has forced physicists to admit that nature does not owe us a simple answer. Dark matter might be simple, or it might be complicated, or it might be something no one has thought of yet. What has not changed is the evidence that dark matter exists. The galaxies still spin too fast. The clusters still hold together. The light still bends. Whatever dark matter is, it is real, it is out there, and it is holding the universe together. The search has just gotten harder. The experiments have gotten more diverse. The parameter space has gotten larger. And the field has learned to be patient. WIMPs might still show up. Axions might convert into photons in a resonant cavity tomorrow. Sterile neutrinos might decay and produce a clear X-ray line. Fuzzy dark matter might reveal itself in the structure of dwarf galaxies. Or the answer might be something else entirely. The one thing the field has learned is that dark matter is not going to announce itself easily. It has been hiding for billions of years. It has refused every attempt to pin it down. It does not glow. It does not collide. It does not leave tracks. It just sits there, invisible and silent, shaping the structure of galaxies and clusters and the cosmic web itself. And whatever it is made of, whatever particles or fields or exotic objects it turns out to be, it is the foundation of everything we see. The stars, the galaxies, the vast filaments stretching across hundreds of millions of light years, all of it built on a scaffold made of something we still do not understand. That scaffold is not going anywhere. It has been there since the beginning. And as the search moves forward, as new experiments come online and new ideas are tested, the hope is that one day the scaffold will finally reveal what it is made of. The search for dark matter particles, whether they turn out to be WIMPs or axions or something no one has thought of yet, is a hunt for the smallest pieces of an enormous puzzle. The individual particles, if we ever catch one, will tell us what dark matter is made of. What it does not tell us, at least not directly, is what dark matter does at the scale of the universe itself. Because dark matter is not just a collection of invisible particles drifting through space. It is the architecture, the framework, the skeleton that everything else is built on. And that skeleton, when you zoom out far enough, reveals a structure so vast and so organized that it forces you to rethink what the universe actually is. Start with a simple question: why are there galaxies at all? Why is matter clumped into stars and planets and solar systems rather than spread out evenly in a thin uniform fog? The early universe, for the first few 100,000 years after the Big Bang, was remarkably smooth. Not perfectly smooth, but close. The tiny variations in density, The places where the matter was slightly denser or slightly less dense were on the order of 1 part in 100,000. That is an absurdly small difference. If you took a cubic meter of space in the early universe and measured how much matter was in it, and then moved 1,000,000 kilometers away and measured again, the two measurements would differ by about 1/100%. That is how smooth things were. And yet today, 14 billion years later, the universe is anything but smooth. Matter is concentrated in galaxies. Galaxies are concentrated in clusters. Clusters are strung along filaments, stretching hundreds of millions of light years. And in between, there are voids. Vast, empty regions where almost nothing exists. The contrast is stark. Some regions of the universe contain thousands of galaxies packed into a volume the size of our local neighborhood. Other regions, just as large, contain maybe a handful. The universe went from nearly uniform to wildly uneven. And the reason that happened, the reason there is any structure at all, is dark matter. Here is the problem ordinary matter had. In the early universe, after the Big Bang, but before stars formed, the cosmos was filled with a hot plasma of protons, electrons, and photons. The photons, particles of light, were constantly colliding with the electrons and protons. Those collisions kept the plasma stirred up. Any region that tried to collapse under its own gravity would immediately get pushed back out by the pressure of all those photons bouncing around. Light, it turns out, is a very effective way to prevent things from clumping. The pressure it exerts is small on everyday scales, but in a dense, hot plasma filling the entire universe, it was enough to stop ordinary matter from collapsing into anything. Gravity was pulling inward. Radiation pressure was pushing outward. And for the first few 100,000 years, radiation won. Then, about 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into hydrogen atoms. That moment is called recombination, and it changed everything. Once the electrons were locked into atoms, they stopped scattering photons. The light that had been trapped in the plasma suddenly broke free and started traveling through space unimpeded. That light is what we see today as the cosmic microwave background. And the moment it escaped, the radiation pressure holding the ordinary matter apart vanished. Gravity could finally take over. Except by that point, it was almost too late. The universe had been expanding for 380,000 years. The tiny density fluctuations from the early universe, the 1 part in 100,000 variations, had not grown much because radiation pressure kept them in check. If all the matter in the universe were ordinary matter, baryonic matter, those tiny seeds would have started collapsing after recombination, but they would have been starting from scratch. And the time between recombination and today, while long by human standards, is not actually that long in cosmological terms. Run the numbers, and it turns out that ordinary matter alone, starting to collapse only after recombination, would not have had enough time to build the structures we see. The galaxies would be smaller, the clusters would be less massive, the cosmic web would be fuzzier and less defined. The universe we observe is too structured, too clumpy, to have formed purely from ordinary matter collapsing under gravity after recombination. Dark matter solved that problem. Dark matter does not interact with photons. It does not scatter light. It does not care about radiation pressure. While ordinary matter was being held in place by the photons bouncing around in the early universe, dark matter was already collapsing. The tiny density fluctuations in the dark matter distribution started growing immediately after the Big Bang. Gravity pulled the denser regions together. Those regions got denser, which made their gravity stronger, which pulled in more dark matter, which made them denser still. A feedback loop. Slowly at first, then faster. By the time ordinary matter was finally free to move, the dark matter had already done most of the heavy lifting. It had collapsed into clumps, halos. Gravitational wells deep enough that when ordinary matter was released from the grip of radiation pressure, it fell straight into those wells. That is why structure formation in the universe required dark matter. Ordinary matter could not get a head start. Dark matter could, and did. By the time the first atoms formed, the scaffolding was already in place. The dark matter halos were sitting there, waiting, their gravity pulling on the surrounding gas. The gas fell in, cooled, condensed, and eventually formed stars. Those stars grouped into galaxies. The galaxies inherited the distribution of the dark matter halos, and that distribution, shaped by 14 billion years of gravitational collapse, is what we see when we map the large-scale structure of the universe today. The process has been simulated thousands of times. Cosmologists take the known properties of dark matter, the fact that it is cold, that it only interacts via gravity, that it was present in specific abundances in the early universe, and they run computer models forward in time. Start with a nearly uniform distribution of dark matter with tiny random fluctuations. Let gravity do its work. Watch what happens. The simulations are enormous. They track billions of particles over billions of years of cosmic time. The computation takes months, sometimes years, even on the fastest supercomputers. And the result, every single time, is the same. The dark matter collapses into a web, not a random web, a specific kind of structure, filaments. Long, dense threads of dark matter stretching across hundreds of millions of light years. Where the filaments intersect, nodes form, dense concentrations where galaxy clusters eventually sit. Between the filaments, voids, huge empty bubbles where dark matter is sparse and galaxies are rare. The simulations produce this structure naturally. You do not have to tell the computer to make filaments. You do not have to tune the parameters to get voids. You start with gravity and dark matter and the initial conditions from the early universe, and the cosmic web emerges on its own. And here is the kicker. When astronomers map the actual distribution of galaxies in the universe, using massive surveys that catalog millions of galaxies across billions of light years, the structure they find matches the simulations almost perfectly. The filaments are there, the nodes are there, the voids are there. The scales match, the density contrasts match, the whole thing lines up. The simulations, which only include dark matter and gravity, predict the large-scale structure of the universe with shocking accuracy. That is not a coincidence, that is confirmation. The cosmic web is real, and it is made primarily of dark matter. Galaxies do not form in isolation. They form inside dark matter halos. Think of a halo as a cloud of dark matter, roughly spherical, with most of the mass concentrated near the center and a long diffuse tail extending outward. The mass of a typical halo can range from millions to trillions of times the mass of the Sun. Our own Milky Way sits inside a dark matter halo, weighing roughly 1 trillion solar masses. The visible part of the galaxy, all the stars and gas and dust, makes up maybe 10% of that. The rest is dark. The halo extends far beyond the edge of the visible galaxy. If you could see dark matter, the Milky Way would look like a tiny glowing seed sitting at the center of an enormous invisible cloud. That cloud is not static. It is pulling on everything inside it. The stars in the galaxy orbit through the halo under its gravitational influence. The flat rotation curves Vera Rubin measured, the ones that pointed to dark matter in the first place, are a direct consequence of the halo's mass distribution. The gas clouds drifting through the galaxy feel the halo's gravity. New stars forming in the galactic disk are born inside a gravitational well carved out by dark matter billions of years ago. The entire structure of the galaxy, the way it spins, the way it holds together, the way it interacts with neighboring galaxies, is determined by the dark matter halo it is embedded in. And those halos are not alone. They sit inside the cosmic web. A galaxy halo might lie along a filament, with dark matter streaming in from either direction. Or it might sit at a node where multiple filaments intersect, surrounded by other halos, part of a galaxy cluster. The location matters. Galaxies in dense environments, at the nodes of the cosmic web, experience more interactions. They collide with other galaxies. They merge. They get stripped of gas by the hot plasma filling the space between galaxies in a cluster. Galaxies in less dense regions, along the filaments or in the voids, evolve more quietly. They accrete gas from the surrounding medium. They form stars at a steady rate. They grow without the violent disruptions that mark life in a cluster. The cosmic web shapes galaxy evolution. It determines where galaxies form, how massive they become, and what happens to them over time. A small dark matter halo sitting in a void might host a single dwarf galaxy that spends billions of years peacefully forming stars. A massive halo at the intersection of several filaments might host a giant elliptical galaxy built from dozens of mergers. The environment, defined by the distribution of dark matter on scales of hundreds of millions of light-years, sets the stage for everything that happens at the scale of individual galaxies. Galaxy mergers are a particularly clear example of dark matter's role. When two galaxies collide, the stars mostly pass through each other. Stars are tiny, and the distances between them are vast. The odds of two stars actually hitting each other during a galactic collision are effectively zero. The gas, however, does collide. It slams together, heats up, and can trigger bursts of star formation. But the dark matter halos do something different. They merge, slowly, over hundreds of millions of years. The two halos, each one a massive cloud of invisible particles, drift together under their mutual gravity. As they merge, they reshape the gravitational landscape. Stars that were orbiting in one galaxy's halo get pulled into orbits around the combined halo. The galaxies themselves, the visible parts, spiral inward and eventually combine into a single larger galaxy. But the merger is driven, from start to finish, by the dark matter halos. The visible galaxies are just passengers. The Milky Way is currently in the process of merging with several smaller galaxies. The Sagittarius Dwarf Elliptical Galaxy, a small galaxy sitting on the far side of the Milky Way's disk, is being torn apart by our galaxy's gravity. Its stars are being pulled into long streams that wrap around the Milky Way multiple times. The process is slow. It will take hundreds of millions of years for Sagittarius to be fully absorbed. But the mechanism is clear. The dark matter halo of the Milky Way is far more massive than the halo of Sagittarius. The smaller halo is being pulled into the larger one. The stars follow, and eventually Sagittarius will disappear, its stars and gas absorbed into the Milky Way, its dark matter halo blended into ours. In about 4 billion years, the Milky Way will collide with Andromeda, the nearest large spiral galaxy. The two galaxies are currently moving toward each other at roughly 110 kilometers per second. The collision is inevitable. When it happens, the dark matter halos will merge first. The stars will take longer. Simulations of the collision show that the two galaxies will pass through each other, then swing back, then pass through again, losing energy each time until they settle into a single massive elliptical galaxy. The process will take billions of years. And through all of it, the dark matter halos will be the dominant gravitational players, shaping the orbits of the stars, defining the structure of the final merged galaxy. The role of dark matter in structure formation goes deeper than just providing gravity. It also sets the initial conditions. The tiny fluctuations in the dark matter density in the early universe, the 1 part in 100,000 variations, were not random. They were imprinted by processes in the first fractions of a second after the Big Bang, during a phase called inflation. Inflation stretched quantum fluctuations to cosmic scales, creating a specific pattern of density variations. That pattern is visible today in the cosmic microwave background as tiny temperature differences across the sky, and it is also visible in the large-scale structure of the universe. The same fluctuations that show up as hot and cold spots in the microwave background are the seeds that grew into the cosmic web. Measuring those fluctuations with precision has allowed cosmologists to constrain the properties of dark matter with remarkable accuracy. The amount of dark matter, the ratio of dark matter to ordinary matter, the fact that dark matter is cold, meaning the particles were moving slowly in the early universe. All of these properties are encoded in the pattern of fluctuations. The cosmic microwave background is essentially a baby picture of the universe, taken when it was 380,000 years old. The large-scale structure of galaxies and clusters is a more recent picture, showing the universe as it is today. Comparing the two, cosmologists can trace how structure grew over time, and the growth rate matches the predictions of cold dark matter almost exactly. There is a caveat. On small scales, below the size of individual galaxies, the simulations and observations do not match as well. The simulations predict that dark matter halos should be full of subhalos, smaller clumps of dark matter embedded within the larger halo. Thousands of them, maybe tens of thousands, orbiting through the main halo like moons around a planet. Each subhalo should, in principle, be able to host a small galaxy. But when astronomers look at galaxies like the Milky Way, they do not find nearly that many satellite galaxies. They find a few dozen, maybe 100 if you count the very faintest ones. That discrepancy is called the missing satellites problem. Either the simulations are wrong and dark matter does not form as many subhalos as predicted, or the subhalos are there but most of them are dark. No stars, no gas, just invisible clumps of dark matter orbiting through the Milky Way's halo, undetectable except through their gravitational influence. A related issue is the core cusp problem. Simulations of cold dark matter halos tend to produce density profiles that rise steeply toward the center, a cusp. The density keeps climbing as you get closer to the middle of the halo. Observations of real galaxies, particularly small dwarf galaxies, often show flatter density profiles at the center, a core. The mismatch is not huge, but it is persistent. Some researchers argue that the problem is not with dark matter, but with how ordinary matter behaves. Gas, stars, and supernova feedback can redistribute mass in the center of a galaxy, flattening the dark matter density profile. Others argue that the mismatch hints at something wrong with cold dark matter, and that warm dark matter or self-interacting dark matter might fit the observations better. These small-scale tensions have not overturned the cold dark matter paradigm, but they have made cosmologists cautious. The large-scale structure, the cosmic web, the formation of galaxy clusters, all of that matches cold dark matter beautifully. The small-scale structure, the centers of galaxies and the populations of satellite galaxies shows some discrepancies. Whether those discrepancies are real problems or just reflect our incomplete understanding of how ordinary matter behaves is still an open question. The simulations track dark matter with extraordinary precision. They are much worse at tracking gas, star formation, and feedback processes because those involve complicated physics that is hard to model. It is entirely possible that once the simulations improve, the small-scale tensions will disappear. What is not in question is that dark matter is essential for structure formation. Without it, the universe would be fundamentally different. The galaxies would be smaller, fewer, and more loosely bound. The clusters would not exist. The cosmic web would be absent. The first stars would have formed later, if they formed at all. Life, which requires heavy elements forged in stars, which requires galaxies to form and persist long enough for those stars to live and die, would have had a much harder time getting started, possibly an impossible time. Dark matter is not just an interesting curiosity or a missing piece of the cosmic puzzle. It is the foundation, the invisible architecture that allows everything else to exist. The cosmic web, the structure that simulations predict and observations confirm, is one of the most striking features of the universe at large scales. If you could see dark matter, if it glowed or emitted some kind of signal, the universe would not look like a collection of isolated galaxies scattered through empty space. It would look like a foam, a three-dimensional network of filaments and sheets, with galaxies strung along the densest parts like beads on a string. The filaments are not empty. They are full of dark matter, streaming along the threads, falling toward the nodes where the filaments intersect. Ordinary matter follows the dark matter. Gas flows along the filaments, funneled by gravity toward the densest regions. Galaxies form where the gas accumulates and cools. The visible universe, the stars and galaxies and clusters, is a tracer, a marker showing where the dark matter is concentrated. The filaments are enormous. Some stretch for more than 1 billion light-years. The density contrast between the filaments and the voids is dramatic. Inside a filament, the density of dark matter is tens or hundreds of times higher than the average density of the universe. Inside a void, the density is 1/10 or less of average. The voids are not completely empty, but they are close. A few small galaxies, a bit of diffuse gas, and not much else. Most of the mass and most of the action is in the filaments and nodes. The cosmic web is not static. It is still growing. Dark matter is still collapsing. Filaments are still funneling matter toward the nodes. Clusters are still merging. The structure we see today is a snapshot of an ongoing process that has been running for 14 billion years and will continue for billions more. Eventually, in the far future, when dark energy has had time to dominate completely, the expansion of the universe will accelerate to the point where the cosmic web starts to tear apart. Clusters will stop merging. Filaments will thin out. Galaxies outside the local gravitationally bound structures will drift out of reach, receding faster than light can travel between them. But that is a story for the deep future. For now, the cosmic web is thriving. And dark matter is the glue, the scaffold, the underlying framework that makes all of it possible. The University of Chicago describes dark matter as an invisible web extending across the universe, creating a scaffold for all the stars and galaxies. NASA calls it the invisible glue that holds the universe together. Both descriptions are accurate, but they are also understated. Dark matter is not just holding things together. It is defining the structure. It is determining where galaxies form, how they evolve, how they interact. It is shaping the large-scale distribution of matter across billions of light-years. It is the reason there is structure at all, rather than a thin, uniform soup of gas and radiation. The universe we see, the stars and galaxies and clusters and filaments, is the visible manifestation of an invisible architecture, a scaffolding built from particles that do not emit light, do not absorb light, and have never been directly detected. And yet that scaffolding is more massive, more widespread, and more fundamental than anything made of ordinary matter. The cosmic web is vast, it is organized, and it is almost entirely invisible. If you could somehow strip away all the ordinary matter from the universe, remove every star and planet and gas cloud and photon, what would be left is the dark matter distribution, the web itself. A three-dimensional network of filaments stretching across the observable universe, connecting clusters and groups and galaxies into a single vast interconnected structure. That structure is not an accident, it is not random. It is the natural outcome of gravity acting on dark matter over billions of years, and it is, in a very real sense, the skeleton of the cosmos. Everything we see is built on top of it: the light, the stars, the galaxies, the planets, the life. All of it resting on a foundation made of darkness. A foundation that spans not just galaxies, but the space between them. A foundation that reaches across distances so vast that light takes hundreds of millions of years to cross them. That foundation is the subject of the next chapter. The cosmic web in all its filamentary, billion light-year glory, the largest structure in the universe, and the clearest proof that dark matter is not just a local phenomenon, not just something that affects galaxies or clusters, but a fundamental organizing principle of the universe itself. The cosmic web is not a metaphor. When cosmologists say the universe is organized like a web, they are not reaching for a poetic comparison or trying to make the science sound more interesting. They mean it literally. The largest structure in the observable universe, spanning billions of light years, is a network, a three-dimensional tapestry of filaments and walls, with enormous voids in between, and galaxies clustered at the intersections. The structure is real, it has been mapped, it has been simulated, and it is almost entirely invisible because the material holding it together, the scaffolding on which everything else rests, is dark matter. If you could strip away every star, every planet, every cloud of gas, every photon of light, what would remain is the skeleton. A vast interconnected framework of dark matter filaments stretching across the cosmos, connecting galaxy clusters the way highways connect cities. Those filaments are not empty. They are full of dark matter, streaming along the threads, funneling toward the densest regions where the filaments intersect, and wherever the dark matter goes, ordinary matter follows. Gas flows along the filaments, pulled by gravity into the same gravitational wells. Galaxies form where the gas accumulates and cools. The visible universe, the part we can photograph and measure and point telescopes at, is a tracer, a set of bright markers showing where the invisible framework is concentrated. The cosmic web is the largest known structure in the observable universe. Nothing bigger has been found, nothing more organized, and nothing more dependent on dark matter. Without dark matter, the web would not exist. The filaments would not form, the clusters would not hold together. The voids would not be nearly as empty. The entire large-scale architecture of the cosmos is a direct consequence of how dark matter behaves under gravity over billions of years. And that architecture, when you map it out, looks strikingly like a foam, or a sponge, or, yes, a web. The analogies vary, but the structure is consistent. Matter is concentrated in sheets and filaments. The spaces in between are sparse, and the pattern repeats across the entire observable universe. The first hints of this structure came in the 1980s, when astronomers started mapping the positions of galaxies in 3 dimensions, not just where galaxies are on the sky, but how far away they are. Measuring distance requires measuring redshift, the stretching of light caused by the expansion of the universe. The further away a galaxy is, the more its light has been stretched toward the red end of the spectrum. By measuring the redshift of thousands of galaxies, astronomers could build a map showing their positions in space, and when they did, the structure that emerged was shocking. Galaxies were not scattered randomly. They were arranged in patterns, long chains, sheets, walls, with enormous empty regions in between. One of the first major surveys to reveal this was the CFA Redshift Survey, led by Margaret Geller and John Huckra at the Harvard-Smithsonian Center for Astrophysics. In 1989, they published a map showing the distribution of galaxies in a slice of the sky. The map looked nothing like what anyone expected. Galaxies were clustered along a thin structure that Geller and Huckra called the Great Wall, a sheet of galaxies stretching more than 500 million light-years across. And around the Great Wall were voids, huge bubbles of nearly empty space where galaxies were rare. The map looked, in Geller's own words, like a slice through a soap bubble, thin walls with empty regions in between. That discovery was the first clear evidence that the universe has structure on scales far larger than individual galaxies or even galaxy clusters. The Great Wall was not a cluster. It was not a supercluster. It was something bigger, a coherent feature stretching across a significant fraction of the observable universe. And it was not alone. As more surveys were completed, more walls and filaments showed up. The structure repeated. Everywhere astronomers looked, they found the same pattern: filaments connecting clusters, voids filling the spaces between, a network spanning the cosmos. The cosmic web is not just visible matter. In fact, visible matter is a tiny fraction of what is there. The filaments themselves are made primarily of dark matter. The mass of the dark matter in a typical filament far exceeds the mass of the gas and stars embedded in it. Estimates vary depending on the region, but the ratio is consistent with the overall cosmic budget. About 85% of the matter in the universe is dark. That ratio holds in the filaments, in the clusters, in the voids, everywhere. The cosmic web is fundamentally a dark matter structure. The galaxies we see are just the bright spots marking where the dark matter is densest. Simulations have been critical for understanding how the web formed. Cosmologists take the initial conditions from the early universe, the tiny density fluctuations visible in the cosmic microwave background, and run them forward in time using the laws of gravity. The simulations track billions of dark matter particles, letting them interact gravitationally, clumping together under their own attraction. No other forces are included, no electromagnetic interactions, no collisions, just gravity. And what emerges, naturally, is the cosmic web. Filaments form. Voids grow. Clusters appear at the nodes where multiple filaments intersect. The structure looks almost identical to what is observed in galaxy surveys. Same filaments, same voids, same clustering. The match is so close that it leaves little doubt. The large-scale structure of the universe is shaped by dark matter. The filaments are enormous. Some stretch for tens of millions of light years. Others reach even further. One filament in the Shapley supercluster, a massive concentration of galaxy clusters about 650 million light-years from Earth, was measured at roughly 23 million light-years long. Another reported filament spans about 50 million light-years. These are not thin threads. They are thick structures containing gas, galaxies, and enormous amounts of dark matter. The gas in these filaments is not cold. Observations of X-ray emission from filament gas show temperatures around 10 million degrees Celsius. The gas is heated by shocks as it falls into the filament and by the gravitational energy released as matter collapses along the thread. The mass of gas in a single large filament can exceed the mass of the Milky Way by a factor of 10 or more, and that is just the gas. The dark matter is far more massive. The filaments are not static, they are active. Matter is streaming along them, flowing toward the densest regions. Dark matter particles are falling inward along the filament, picking up speed as gravity pulls them toward the nodes. Gas follows, funneled by the gravitational potential carved out by the dark matter. Galaxies themselves move along the filaments, some toward clusters, others being pulled into interactions with neighboring galaxies. The cosmic web is not a frozen structure. It is dynamic, evolving, still growing. One of the most surprising discoveries about the filaments came in 2021, when a team of researchers reported that at least one massive filament appears to be rotating. The filament, part of a structure connecting several galaxy clusters, was found to have a coherent rotation speed of about 110 kilometers per second. That is slow by cosmic standards, but it is measurable. And it is significant because it means the filament is not just collapsing inward under gravity. It has angular momentum. The rotation likely arose from tidal torques in the early universe, small twists imparted by neighboring structures. Those twists, amplified over billions of years, turned into a slow spin. The discovery suggests that large-scale structure in the universe is even more organized than previously thought. Not just clumpy, but rotating. Not just connected, but coherent. The voids are the other half of the story. They are the regions between the filaments, the bubbles in the foam. Voids are not completely empty. They contain some galaxies, a bit of gas, and presumably dark matter, though much less than in the filaments. The density of matter in a void can be a tenth or less of the average density of the universe. That makes them sparse, but not absent. A typical void might span 100 to 300 million light-years. The largest known voids are even bigger. Some reach diameters of more than 1 billion light-years. These are regions where almost nothing happens. No major star formation. Few galaxy interactions. Just quiet, empty space. The existence of voids is as important as the existence of filaments. They show that the universe is not just clumpy, it is organized into two distinct environments. Dense regions where matter accumulates and sparse regions where it does not. That dichotomy is a direct consequence of how gravitational collapse works. Matter flows out of underdense regions and into overdense ones. The underdense regions get emptier. The overdense regions get denser. The process is self-reinforcing. Over time, the contrast between the dense filaments and the empty voids grows. The structure becomes more pronounced. The cosmic web sharpens. The voids play a role in cosmic evolution. Galaxies in voids tend to be smaller, less massive, and less active than galaxies in denser regions. They form stars more slowly. They undergo fewer mergers because there are fewer neighbors to merge with. The environment shapes their evolution. A galaxy sitting in a void experiences a fundamentally different history than a galaxy sitting in a filament or a cluster. The large-scale structure of the universe is not just a backdrop. It actively influences what happens to the galaxies embedded in it. The relationship between filaments, clusters, and voids is tightly connected. Clusters form at the nodes where multiple filaments intersect. The filaments act as highways, channeling matter into the clusters. The clusters are the densest regions of the cosmic web, containing hundreds or thousands of galaxies packed into volumes only a few million light-years across. The density contrast between a cluster and a void is extreme. A cluster might have 1,000 times more matter per unit volume than a void. That contrast is what defines the cosmic web. It is not just structure. It is structure with enormous variation in density. The Milky Way sits inside a region of the cosmic web called Laniakea. The name, chosen by a team of astronomers in 2014, comes from the Hawaiian words for immeasurable heaven. Laniakea is a supercluster, a collection of galaxy groups and clusters, all connected by filaments of dark matter. It spans about 520 million light-years and contains roughly 100,000 large galaxies. The Milky Way is not at the center. It sits near the edge, in a relatively quiet part of the superstructure. The gravitational center of Laniakea, the point where all the matter in the region is slowly being pulled toward, is called the Great Attractor. It is a massive concentration of galaxies sitting about 250 million light-years away, hidden behind the plane of the Milky Way. The Great Attractor itself is being pulled toward an even larger structure, the Shapley supercluster, which lies beyond it. The cosmic web is hierarchical. Small structures are embedded in larger ones. Filaments connect to bigger filaments. Clusters merge into superclusters, and the whole thing is interconnected. Mapping the cosmic web in detail has required enormous surveys. The most ambitious of these is DESI, the Dark Energy Spectroscopic Instrument, mounted on a telescope in Arizona. DESI is designed to measure the redshifts of tens of millions of galaxies and quasars, building a three-dimensional map of the universe across billions of light-years. As of the most recent reports, DESI has mapped about 47 million galaxies and quasars, making it the largest three-dimensional map of the cosmos ever created. The map extends back roughly 11 billion light-years, covering a significant fraction of cosmic history. The goal is not just to map where galaxies are, but to measure the expansion history of the universe using a feature called baryon acoustic oscillations. Baryon acoustic oscillations, or BAO, are a relic of the early universe. In the first few 100,000 years after the Big Bang, sound waves propagated through the hot plasma filling space. Those sound waves created a characteristic scale, a preferred distance at which matter likes to cluster. That scale is imprinted in the distribution of galaxies today. It shows up as a small excess in the number of galaxy pairs separated by about 500 million light-years. That excess is faint, but it is detectable if you measure enough galaxies, and it is useful because the BAO scale is a standard ruler. It was set in the early universe, and it has been stretched by the expansion of space ever since. By measuring how much the BAO scale has been stretched at different distances, astronomers can trace how fast the universe has been expanding at different times. That measurement is one of the best ways to constrain dark energy, the mysterious force accelerating the expansion. But the BAO signal also traces the cosmic web. It is another way to see the large-scale structure, another confirmation that the filaments and voids are real. The cosmic web is consistent with a principle cosmologists rely on, called the cosmological principle. The principle states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in all directions. That seems wildly inconsistent with the cosmic web. Filaments, voids, clusters, none of that looks smooth or uniform. But the key phrase is on sufficiently large scales. If you zoom out far enough, if you average over volumes larger than 1 billion light-years or so, the structure smooths out. The number of galaxies per unit volume becomes roughly constant. The density fluctuations fade. The universe stops looking like a web and starts looking like a uniform sea. The cosmic web is structure on intermediate scales, large enough to span hundreds of millions of light-years, but not so large that it violates the overall smoothness of the universe. That smoothness is not an accident. It is a consequence of the initial conditions. The universe started out nearly uniform. The tiny density fluctuations in the early universe, the 1 part in 100,000 variations, grew under gravity into the structures we see today. But they grew from a smooth starting point. The cosmic web is not evidence that the universe is fundamentally lumpy. It is evidence that gravity, acting over billions of years, amplifies tiny differences into large structures. The process is well understood. The simulations match the observations. The cosmic principle holds. The intergalactic medium, the gas filling the space between galaxies, is deeply connected to the cosmic web. Most of that gas sits in the filaments. It is not cold. It is not dense enough to form stars. It is warm or hot, heated by the gravitational collapse of the structure itself. When gas falls into a filament or into a cluster, it releases gravitational potential energy. That energy heats the gas. In clusters, the gas can reach tens of millions of degrees, glowing brightly in X-rays. In filaments, the gas is cooler, a few million degrees, but still hot enough to emit faint X-ray signals that have been detected by space-based telescopes. The gas in the filaments is a record of the cosmic web's growth. It shows where matter has been funneled, where structures have formed, where the dark matter is concentrated. The gas also feeds galaxies. Galaxies sitting in filaments can accrete fresh gas streaming along the thread. That gas cools, falls into the galaxy, and fuels new star formation. The process is called cold mode accretion, and it is thought to be the primary way galaxies in the early universe grew. Today, most large galaxies have shut off their cold accretion because they sit in hot halos where the infalling gas gets heated too much to cool and condense. But smaller galaxies and galaxies in less dense environments are still accreting gas from their surroundings. The cosmic web is not just structure, it is a supply chain. It channels gas from the voids into the filaments and from the filaments into galaxies. The structure feeds the growth. The cosmic web is still evolving. It is not finished. Gravity is still pulling matter into the filaments. Clusters are still merging. Voids are still growing. The structure we see today is a snapshot of an ongoing process that has been running for 14 billion years and will continue for billions more. Eventually, far in the future, dark energy will dominate completely. The accelerating expansion of the universe will overcome the gravity holding structures together. The cosmic web will start to thin out. Filaments will weaken. Clusters will stop merging. Galaxies outside gravitationally bound groups will drift out of reach, receding faster than light. The structure will fade, but that is a story for the distant future. For now, the cosmic web is thriving. It is growing. It is the dominant feature of the universe on the largest scales we can observe. The web is also a challenge for observations. The filaments are faint. The gas in them is sparse and hot, difficult to detect unless you have sensitive X-ray telescopes and long observation times. The dark matter, of course, is completely invisible. The only way to map the web in detail is to map the galaxies and use them as tracers. That requires enormous surveys covering large fractions of the sky and measuring redshifts for millions of objects. The technology has only recently caught up to the task. DIDZ is one example. The Sloan Digital Sky Survey, which ran for more than 2 decades, was another. These surveys have produced maps of the cosmic web that are stunning in their detail. You can see the filaments, you can see the voids. You can trace the connections between clusters. The structure is no longer theoretical. It is observed, mapped, and measured. One of the striking features of the cosmic web is its coherence. The filaments are not short. They are not disconnected. They stretch for tens or hundreds of millions of light years, linking clusters that are separated by vast distances. The web is truly a web. It is interconnected. The structure on one side of the sky is connected through a chain of filaments to structure on the other side. The universe is not a collection of isolated islands. It is a single vast network, and that network is held together by dark matter. The filaments are dark matter. The nodes are dark matter. The scaffolding is dark matter. The visible matter, the galaxies, the gas, the stars, all of it is resting on a framework made of something we cannot see and do not fully understand. The cosmic web forces a shift in perspective. When you look at an image of a galaxy, you see stars, billions of them. You see spiral arms, or elliptical halos, or irregular clumps of light. What you do not see is the halo of dark matter surrounding the galaxy, the invisible cloud that outweighs the visible stars by a factor of 10. You do not see the filament the galaxy is embedded in, the stream of dark matter funneling matter toward the cluster the galaxy is heading for. You do not see the void on the other side, the empty region the galaxy is moving away from. The image shows you the light. The structure underneath, the architecture holding it all together, is invisible. That invisibility is why dark matter went undetected for so long. The cosmic web is vast, it is organized, it is the largest structure in the universe. And until astronomers started mapping galaxies in 3 dimensions, until they started running simulations and comparing them to observations, the web was completely hidden. The galaxies were visible, the clusters were visible. The structure connecting them, the scaffolding they were hanging from, was not. It took decades of painstaking work to reveal it. And even now, with the maps and the simulations, the web itself remains invisible. We see its effects, we trace its outline, but the substance, the dark matter that makes up the bulk of it, has never been directly observed. The cosmic web is the clearest evidence that dark matter is not just a local phenomenon. It is not just something affecting individual galaxies or even galaxy clusters. It is a fundamental organizing principle of the universe. The web spans billions of light years. It connects structures across the entire observable cosmos, and it is made primarily of dark matter. Roughly 85% of the matter holding the web together is invisible. That is not a small correction. That is not a minor adjustment to the models. That is the dominant component, the foundation, the framework on which everything else is built. And yet, despite its dominance, despite its role in shaping the largest structures in the universe, dark matter remains a mystery. We know it is there because of what it does. It holds galaxies together. It bends light. It creates the cosmic web, but we do not know what it is. We do not know what particles it is made of. We have not detected those particles in a lab. We have not confirmed them in an underground detector or a particle collider. The web is real. The evidence is overwhelming. The mystery remains unsolved. The cosmic web is not the end of the story. It is a clue, a massive, billion light-year clue stretching across the observable universe, pointing towards something fundamental about the nature of matter and gravity and the evolution of the cosmos. The web shows us where dark matter is. It shows us how dark matter behaves. It shows us what dark matter does. What it does not show us is what dark matter is. That answer, if it comes, will come from the experiments and observations pushing forward right now. The underground detectors waiting in the dark, the particle colliders smashing protons together at record energies, the telescopes mapping the sky with unprecedented precision. Somewhere in that data, in that noise, in that vast sea of measurements, the identity of dark matter might finally reveal itself. The cosmic web is waiting. The structure is there. The scaffolding is holding. And the question, the 85% question, is still unanswered. The cosmic web stretches across billions of light years. A vast, invisible framework made almost entirely of dark matter, holding galaxies in place, shaping the large-scale structure of everything we see. It is the skeleton of the universe. And after nearly a century of looking, after mapping the filaments and measuring the lensing and confirming the effects in 1,000 different ways, we still do not know what the skeleton is made of. Not with certainty. Not in a way that would let us point to a particle in a detector and say, that is it, that is dark matter. That gap between knowing something exists and knowing what it is has defined the field for decades, and it is not closing as fast as anyone hoped. The underground detectors have been running for years. The experiments have gotten more sensitive. The backgrounds have been reduced to near nothing, and the signal, the one clear, unambiguous detection of a dark matter particle interacting with ordinary matter, has not shown up. Not in a xenon tank buried under a mile of rock, not in a microwave cavity tuned to catch axions, not in a particle collider smashing protons together at energies high enough to create particles that have never existed since the early universe. The searches have ruled out enormous swaths of parameter space. They have narrowed the possibilities. They have confirmed that if dark matter is there, it is hiding better than anyone expected, but they have not found it. That does not mean the search is over. It means the search is getting harder, and in some ways more interesting. Because the null results, the decades of coming up empty, have forced the field to broaden, to look in new places, to consider alternatives that would have seemed too exotic or too unlikely 10 years ago. The WIMP hypothesis dominated the field for a long time because it fit so neatly. WIMPs emerged naturally from supersymmetry, a well-motivated extension to the standard model. They had the right properties to explain the cosmic abundance of dark matter. They were heavy enough to be cold, meaning they moved slowly and clumped like observations required, and they were detectable, at least in principle. Build a sensitive enough detector, wait long enough, and a WIMP would eventually bump into a nucleus and announce itself. That was the promise. The experiments were built around that promise, and the promise has not been kept. So the field is pivoting, not abandoning WIMPs entirely, but expanding the search. Future direct detection experiments are being designed with even greater sensitivity, pushing into regions of parameter space that current detectors cannot reach. The next generation of xenon-based experiments, successors to Liux's Zeppelin and Xenon, are being planned with target masses 10 or 20 times larger, 50 tons of liquid xenon instead of 5. The idea is simple. If dark matter interacts more weakly than the simplest models predicted, you need more target material and longer observation times to have a chance of seeing an event. Scale up and the odds improve. The challenge is that as you scale up, the backgrounds get worse. More material means more potential for radioactive contamination. Larger detectors mean more shielding, more purification, more complexity. And there is the neutrino flaw. The point at which neutrino interactions, which look almost identical to WIMP interactions, start showing up at a rate high enough that distinguishing dark matter from neutrinos becomes statistically difficult. The neutrino flaw is not a hard wall, it is more like a fog. Once you reach it, you can still see signals, but identifying which signals are dark matter and which are neutrinos requires careful analysis. You need to look for patterns, directional information, seasonal variations. The Earth moves through the dark matter halo as it orbits the Sun, and that motion should produce a small annual modulation in the dark matter signal. The rate of interactions should peak in June, when the Earth is moving fastest through the halo, and dip in December, when it is moving slowest. Neutrinos, by contrast, do not care about the Earth's motion through the galaxy. Their rate tracks the Sun, not the halo. With enough data, the two signals can be separated, but it requires years of observation and enormous statistical precision. Some experiments are trying a different approach entirely. Instead of building bigger detectors, they are building directional detectors. Detectors that can measure not just the energy deposited by a recoiling nucleus, but the direction the nucleus recoiled in. If a WIMP hits a nucleus, the recoil should point roughly in the direction the Earth is moving through the dark matter halo. That direction changes throughout the day as the Earth rotates. A directional signal would be a smoking gun. Neutrinos produce recoils in random directions. Dark matter, because of the Earth's motion, should produce a preferred direction. The problem is that directional detection is hard. You need a low-density target so the recoiling nucleus has room to move before it collides with something else. That means gas instead of liquid. Gas has far fewer atoms per unit volume, which means far fewer interactions. The event rate drops. The detectors have to be larger to compensate. And measuring the direction of a recoil in a gas detector is technically challenging because the recoil tracks are tiny, micrometers. Measuring them requires exquisite spatial resolution. Several experiments are working on this. Drift, A detector in the United Kingdom uses a time projection chamber filled with a low-pressure gas and tracks recoiling nuclear with sensitive readout electronics. New Age in Japan takes a similar approach. Both are proof-of-concept experiments, demonstrating that directional detection is possible. The next step is scaling up to large enough volumes that the event rate becomes useful. That is still years away. But if it works, if a future directional detector sees a clear signal pointing in the direction of the Earth's motion through the halo, the discovery would be unambiguous. No neutrino background would mimic that signal. It would be dark matter, plain and simple. Axion searches are advancing in parallel. ADMX, the leading axion detector, continues to scan the parameter space frequency by frequency. The experiment has ruled out large portions of the classic QCD axion range, the region where axions are most likely to exist if they solve the strong CP problem and make up dark matter. But the range is large and the scan is slow. Each frequency requires weeks or months of observation. Covering the full range could take decades, so other experiments are being built to speed up the search. Haystack covers higher frequencies. Abracadabra looks for much lighter axions using a completely different detection method based on magnetic flux. The Axion dark matter experiment has proposed upgrades that would allow it to scan faster by using multiple cavities in parallel, and international collaborations are discussing next-generation facilities that would combine multiple detection techniques in a single coordinated effort. The challenge with axions, as with WIMPs, is that the parameter space is vast. Axion masses could range from a millionth of an electron volt up to a thousandth of an electron volt or more. That is 6 orders of magnitude. Searching the entire range requires different experiments optimized for different mass ranges. And even within a given range, the axion coupling strength, the parameter that determines how often an axion converts into a photon, is not known. It could be at the level predicted by the simplest models, or it could be weaker. If it is weaker, the signal is fainter, and the experiments need to be more sensitive. The field is methodically working through the possibilities, but the work is painstaking, and the answer, if it comes, might not come for another decade or more. Indirect detection is the third major avenue. Instead of trying to catch dark matter particles directly, indirect detection looks for the products of dark matter annihilation or decay. If dark matter particles collide with each other in regions where they are densely concentrated, they might annihilate, converting their mass into energy in the form of gamma rays, neutrinos, or other particles. Those particles would then travel through space and could be detected by telescopes or particle detectors on Earth or in orbit. The challenge is that the annihilation rate depends on the density of dark matter squared. The denser the region, the higher the rate. That means the best places to look are the centers of galaxies, where dark matter halos are most concentrated, or in smaller nearby dark matter clumps called subhalos. The galactic center is one obvious target. The Milky Way's central region should contain a dense concentration of dark matter. If WIMPs are annihilating there, the gamma-ray signal would be detectable. The Fermi Gamma Ray Space Telescope has been searching for this signal for more than a decade. In the mid-2010s, a group of researchers reported an excess of gamma rays coming from the galactic center, dubbed the galactic center excess. The signal had the right energy spectrum and spatial distribution to be consistent with WIMP annihilation. For a while, it looked promising. Then further analysis suggested the excess could be explained by a population of unresolved millisecond pulsars, rapidly spinning neutron stars that emit gamma rays. The debate is still ongoing. Some researchers think the signal is dark matter. Others think it is astrophysical. The uncertainty comes down to how well we understand the background sources in the galactic center, which is a messy, complicated region full of stars, gas, and high-energy processes. Dwarf spheroidal galaxies are another target. These are small satellite galaxies orbiting the Milky Way. They contain very few stars and almost no gas, which makes them relatively clean environments, but they are thought to contain large amounts of dark matter, enough to hold the stars together gravitationally. If dark matter is annihilating in these dwarfs, the gamma-ray signal should be detectable with no messy astrophysical backgrounds to confuse things. Fermi has been observing dozens of dwarf galaxies for years. So far, no clear signal has emerged. The null results are constraining. They rule out certain types of WIMPs with high annihilation rates, but they do not rule out all WIMPs. If the annihilation rate is lower than the simplest models predicted, the signal would be too faint to see with current instruments. Neutrino telescopes are looking for dark matter annihilation in the Sun. The idea is that dark matter particles passing through the Sun occasionally collide with the Sun's atoms and lose energy. Some of those particles get gravitationally captured, falling into orbits around the Sun's core. Over time, dark matter accumulates in the center of the Sun. If the density gets high enough, the dark matter particles start annihilating with each other, producing high-energy neutrinos. Those neutrinos travel outward from the Sun and can be detected by neutrino observatories on Earth. IceCube, a massive neutrino detector buried in the ice at the South Pole, has been searching for this signal. No excess has been found. The null result places limits on how strongly dark matter interacts with ordinary matter. If the interaction were strong enough to allow significant capture in the Sun, the neutrino signal should be visible. It is not. So either the interaction is weaker, or dark matter is not WIMPs, or the annihilation products are something other than neutrinos. The lack of a clear indirect detection signal is frustrating, but it is also informative. It tells us that if dark matter is annihilating or decaying, the rate is low enough that current instruments are not sensitive enough to see it. That does not rule out dark matter. It just rules out specific models with high annihilation or decay rates. The field is left in the same position as direct detection, narrowing the parameter space, constraining the possibilities, but not yet finding the particle itself. The next generation of telescopes will play a critical role in the search, not by detecting dark matter particles directly, but by mapping the distribution of dark matter with unprecedented precision. The James Webb Space Telescope is already contributing. Webb's sensitivity to infrared light allows it to observe distant galaxies with extraordinary clarity, and many of those galaxies sit behind massive foreground clusters that act as gravitational lenses. By studying how the background galaxies are distorted, astronomers can map the distribution of dark matter in the foreground clusters in exquisite detail. Some of the lensing maps produced by Webb are so precise that individual clumps of dark matter within clusters can be identified. That level of detail was not possible before. It is allowing researchers to test predictions about how dark matter behaves on small scales, predictions that differ depending on whether dark matter is cold, warm, or self-interacting. The Vera the 100th. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will begin operations in the mid-2020s. The observatory will conduct a 10-year survey of the entire southern sky, imaging billions of galaxies and measuring their shapes with high precision. That data will be used to map weak gravitational lensing across enormous volumes of space. Weak lensing, the subtle distortion of galaxy shapes caused by foreground dark matter, is one of the most powerful tools for measuring the distribution of dark matter on large scales. The Rubin Observatory survey will produce the most detailed map of the cosmic web ever created, tracing the filaments and voids across billions of light years. It will also measure how the dark matter distribution has evolved over time by comparing nearby structures to distant ones. That evolution is sensitive to the properties of dark matter. Cold dark matter produces one pattern. Warm dark matter produces another. The data will constrain which models fit. Euclid, a European Space Agency mission launched in 2023, is doing similar work. Euclid is a space telescope designed to map the geometry of the universe by measuring the positions and shapes of billions of galaxies. Like the Rubin Observatory, Euclid will use weak lensing to trace dark matter. The advantage of a space-based telescope is that it avoids the atmospheric blurring that affects ground-based observations. The disadvantage is that it covers a smaller area of sky. Between Euclid and Rubin, the next decade will produce a flood of data about the large-scale distribution of dark matter. That data will not tell us what dark matter is made of, but it will tell us how it behaves, and that behavior is a critical clue. The potential for dark matter to reveal new physics beyond the Standard Model is one of the most exciting aspects of the search. The Standard Model is extraordinarily successful. It describes every known particle and force with remarkable precision, but it is incomplete. It does not include gravity. It does not explain why neutrinos have mass. It does not explain the matter-antimatter asymmetry in the universe, and it does not include dark matter. That incompleteness is not a flaw, it is an opportunity. Whatever dark matter turns out to be, it will require an extension to the Standard Model. New particles, possibly new forces, possibly new symmetries. The discovery of dark matter will not just solve the mystery of what 85% of the matter in the universe is made of. It will open the door to a deeper understanding of the fundamental laws of physics. Supersymmetry was the leading candidate for that extension for a long time. Supersymmetry predicts that every known particle has a heavier supersymmetric partner. The lightest of those partners, the neutralino, would be stable, massive, and weakly interacting. A perfect WIMP. The Large Hadron Collider at CERN has been searching for supersymmetric particles since it began operations in 2008. So far, nothing has been found. The null results have pushed the predicted masses of supersymmetric particles higher and higher. If supersymmetry exists, the particles are heavier than the simplest models suggested. That does not rule out supersymmetry entirely, but it makes it less attractive. The theory was supposed to predict particles at energies the LHC could reach. The fact that they have not shown up is a problem. Other extensions to the Standard Model are being considered. Extra dimensions, where dark matter is a particle confined to a higher dimensional space that only interacts with our three-dimensional universe through gravity. Portal models, where dark matter lives in a hidden sector connected to the Standard Model by a faint mixing term. Composite dark matter, where dark matter is not a fundamental particle but a bound state of other particles, similar to how protons are bound states of quarks. Each idea is speculative, each has its own theoretical challenges, but all of them share a common feature. They predict that dark matter is not alone. If there is a hidden sector, there are probably multiple particles in it. If dark matter is composite, there are constituents. The discovery of dark matter might not be a single particle. It might be the first glimpse of an entire new layer of physics that has been sitting underneath the Standard Model all along. The philosophical implications of an invisible universe are profound. For most of human history, astronomy was the study of light, the stars, the planets, the galaxies. Everything we knew about the cosmos came from photons arriving at our eyes or our telescopes. That paradigm worked beautifully for thousands of years. It let us map the solar system, discover distant galaxies, measure the expansion of the universe, trace the history of the cosmos back to the Big Bang. And then, in the mid-20th century, we realized that most of the universe does not emit light. Most of the matter is invisible. It does not shine, it does not glow, it does not interact with photons in any way. The foundation of astronomy, the assumption that the universe reveals itself through light, turned out to be incomplete. We were looking at the bright spots and missing the scaffolding underneath. That realization forced a shift. Astronomy became astrophysics. The field stopped being purely observational and became theoretical. You could not see dark matter, but you could infer it. You could measure its effects. You could calculate its distribution. You could simulate its behavior. The tools changed. Gravitational lensing, galaxy dynamics, computer simulations, statistical analysis. The field adapted, and in the process, it became more powerful. The invisible universe is not inaccessible. It is just harder to study. It requires indirect methods, patience, precision, and a willingness to accept that most of what exists is hidden from direct view. That hidden nature is humbling. We live in a universe where the vast majority of the matter is something we have never touched, never seen, never directly detected. We are surrounded by it. It is streaming through our bodies right now. Trillions of dark matter particles passing through every second, and we cannot feel them, cannot measure them individually, cannot catch them, despite building some of the most sensitive instruments humanity has ever constructed. The universe is not obligated to reveal itself easily. It is not obligated to reveal itself at all. The fact that we have been able to infer the existence of dark matter, to measure its abundance, to map its distribution, to trace the cosmic web it creates, is a testament to the power of the scientific method. Observation, inference, hypothesis, testing. The process works even when the thing you are studying refuses to cooperate. The enduring spirit of scientific exploration is what keeps the search going. The underground detectors will keep running. The experiments will keep improving. The sensitivity will keep increasing. The parameter space will keep shrinking. And one day, maybe soon, maybe decades from now, someone will see a signal, a flash of light in a xenon detector, a resonance in a microwave cavity, a gamma-ray excess that cannot be explained by any known astrophysical source, a neutrino signal pointing back to the galactic center. Something, and that something will be the first direct confirmation of what dark matter is made of. The field has been chasing that moment for nearly a century. It has not arrived yet, but the tools are getting better. The experiments are more sensitive. The theoretical models are more refined. The searches are more diverse. The mystery is unfolding. Slowly, the evidence for dark matter has only gotten stronger over the decades. The rotation curves still do not match the visible matter. The clusters still hold together. The light still bends. The cosmic web still spans billions of light years. Every new observation confirms that dark matter is real. Every null result from the detectors confirms that it is elusive. The two facts sit side by side, equally solid. Dark matter exists. Dark matter is hiding. The tension between those facts is what drives the field forward, and the implications extend beyond dark matter itself. Whatever dark matter turns out to be, it will change how we think about the universe. If it is WIMPs, if supersymmetry is real, that opens the door to a whole new set of particles and forces. If it is axions, that confirms a solution to one of the deepest puzzles in particle physics and potentially reveals a new ultralight sector. If it is something else entirely, something no one has thought of yet, that might require rethinking fundamental assumptions about how particles and forces work. The discovery will not just answer the question of what 85% of the matter in the universe is made of. It will answer questions we have not even learned to ask yet. The The search is ongoing, the detectors are running, the surveys are mapping, the simulations are refining. And somewhere in the data, in the noise, in the vast flood of measurements pouring in from telescopes and experiments around the world, the answer is waiting. Dark matter has been hiding for billions of years. It has shaped the universe. It has built the cosmic web. It has held galaxies together. And it has done all of that without emitting a single photon. The scaffolding is invisible, but it is there. And the question of what it is made of is one of the biggest unsolved problems in all of science. The answer, when it comes, will not just solve a mystery. It will rewrite the foundation of cosmology and particle physics. It will reveal the invisible universe, and it will confirm once again that the cosmos is stranger and more wonderful than we ever imagined. The search continues, the mystery unfolds, and the universe, vast and dark and full of secrets, waits. We have spent nearly a century staring at the universe and slowly realizing that most of it has been staring back in silence. The galaxies spin too fast. The clusters hold together against all expectation. The light bends around objects we cannot see. And the cosmic web, that vast billion light-year scaffold stretching across the observable universe, is built almost entirely from something that refuses to announce itself. 85% of all the matter holding everything together is invisible, not hidden behind a cloud or tucked away in some distant corner, invisible by nature, transparent to every form of light humanity has ever learned to detect. That is not a small gap in our knowledge. That is not a footnote waiting to be filled in. That is the foundation, the architecture underneath everything we see. And after 100 years of searching, after building detectors sensitive enough to catch a whisper in the dark, after mapping the distribution of mass across billions of light years with gravitational lensing and galaxy surveys and computer simulations, we still cannot tell you what it is made of. We know it is there. We know how much of it there is. We know what it does. We do not know what it is. The search is not over. The experiments are running. The parameter space is shrinking. And somewhere in the data piling up in labs buried under mountains and in telescopes orbiting far above the atmosphere, the answer might already be waiting. Or it might take another decade or another century. The universe has been patient. It has kept this secret for 14 billion years. It is not in a hurry to give it up, but the question remains, hanging in the dark, louder than any answer we have found so far. If 85% of the universe is invisible, what else are we missing? As new surveys map invisible structure and experiments listen beneath the noise, follow the evidence, because the next faint signal may change what matter means.